Is it visible now?
Still not. Yes, Naveen. It
Yeah.
started. Yeah.
Okay. So this is the title slide you should be able to see.
No, you have.
Uh,
Yes, yes.
yeah. Okay. So basically this is on grant free access in 5G and 5G plus, that is beyond 5G uplink. And I would like to thank my PhD student, especially for these set of slides and the work also, because these set of slides contain some of my research, that is, and most of that research is done with the PhD student, Ms. Harini GS here. So I would like to acknowledge her contribution in making the slides and also in deriving a lot of the results which are a part of these slides. With that small introduction, let's start with what is grant-based access, or how users access the network. So I think it's good that I already discussed these aspects in my previous session. So as we know, after the mobile device gets the synchronization signals from the base station, the first thing it does is it sends something called a random access preamble, that is typically denoted as message 1 in both LTE and 5G. And then base station sends a response which is called the random access response. Then UE sends that I want to get transmit my data, I want a connection request. And then base station responds telling, okay, I identified you, here is your connection setup. And after that, it will also give this uplink grant. Some intermediate messages you can leave out. This base station tells the UE where to transmit the data. This we covered yesterday also. Then the connection will be complete, and afterwards UE will start transmitting its data. So it's a long process. As I told you, it takes like 5 messages to for a UE to start transmitting data with the base station. Okay, and this kind of procedure is called grant-based access. That is because the base station is only providing a grant as where the mobile has to transmit its data. Look at this information here, like uplink grant, there is one of the messages, right? That's how base station provides the grant. Here is your time symbol, here is your subcarriers, on this only you should transmit me data. So that's how it is done in LTE and also in 5G NR. However, 5G NR has improved a little bit, which I will cover soon. So now let's quickly see how random access is done in LTE and also in NB-IoT. NB-IoT is narrowband IoT, which is very similar to LTE, but it is there to support IoT devices. Okay. So in LTE, that random access preamble that I told you will consist of a CP and a long sequence. That's usually a Z2 sequence. There is a name for this sequence. It's called Z2 sequence. It's of length 839 and it has a cyclic prefix and some guard time. And they send this each user.
Naveen, are you
Yeah,
moving your slides?
yeah. I am on the third slide now.
No, but slides are not moving in here.
Oh, did you get the second one?
No, no, it's still on the title screen.
Oh, okay. Maybe I'll stop and share again.
Yeah. Naveen,
Yeah.
when you share that as a window, not as a screen.
Oh, okay, fine. Okay. Uh, are you able to see now?
I think you have started to share. It has to load.
We had some problem with PPT yesterday, so I made it PDF today so that it is
Yeah, yeah.
more
I think,
compatible.
yeah, that's fine. Just once if you share the PDF window, the Acrobat window, it will move.
Yeah, I have shared it.
Yeah, it will load in 2-3 minutes. Yeah, I think now some of the participants are able to see your screen. Maybe from my side, it might get delayed.
Okay. So they are.
Then one of the participants who said that. Okay. Mm, yeah, some of them are able to see, some of them are not allowed. That depends on their bandwidth.
Oh, okay.
That's fine. So Ravi, you have mentioned you are able to see the screen. Now, and Naveen, just you move the window. Let him see if it is moving.
Yeah. Now I moved to slide number 3.
Okay, Ravi, are you able to see slide number 3?
It's called random access in LT, the heading.
Yeah. For others, that will take 2-3 minutes time.
Maybe you can share this PDF. I sent it to you. I will always tell that I'm on slide 3, slide 4, and I can continue.
Yeah. Okay.
So that they can also open it in a window parallelly.
Okay. Fine. Yeah. Okay. That's fine. Okay. Those who have joined with the given credentials, you will be able to see in the files, materials. You can see, I think Naveen, it started to share.
Okay, okay.
But Naveen, still, are you using the browser
Yeah, because I have some problem with the
app? Okay.
app. It is not opening at all.
Okay. Okay. Then if we join the browser, this problem is evident. Yeah.
Maybe I'll just try the app again. Let's give me just 2 minutes.
Yeah.
I'll
No problem. Just
log
you
off
try.
and try again.
Yeah. Meanwhile, I can share the slides too. Okay, so I have sent the slide by email. Either you can take participants can take it by from the email, or those who have joined with the credentials should be able to access from the files, class materials. Inside that, the slides grant free access for 5G. That's the name of the file. You can open that. In case if the problem persists, then you can go ahead with the slides, and where Naveen will be pointing out the slide number, and we'll all follow with our own local copy of it. I have shared by mail, but Veerama, you will be able to get it from the portal also, since you have joined with IIT credentials. Just go to files, class materials, there you can see the file.
Yeah. Hello everyone. Yeah, I think now I was able to log in through the app and you're able to see the second slide now, right? This is the grant-based access which I was talking about. Message 1, which is the random access preamble. Message 2, which is the response from the base station. Then you ask for connection request. It says connection is set up and here is your uplink grant. That is why it's called grant-based access. Now, what is sent in that random access preamble? That differs from standard to standard. That's why I have this third slide here where what is random access in LTE, what is random access in NB-IoT, they are different. So typically in LTE and in LTE advanced, we just send a sequence as a preamble. What is that sequence? It's something called a Z(of)2 sequence. It's already given in the standard. It's a very famous class of sequences. You can read about it offline. So basically the length of the sequence will be a prime number in a Z(of)2 sequence. You pick that sequence, add the cyclic prefix and send it across. Now you might ask, what if two users pick the same sequence? Because only 64 such sequences are available. So if there are many users coming, there is always a finite probability that two users will pick the same sequence. Then of course there will be collision. Base station cannot detect one of them or even both of them depending on the channel conditions. And in that case, they won't get that random access response. Both will not get that response. So that way it knows that my signal has not been detected and tries after some time. So there is a back off time. Randomly both of them will back off for some duration and try again. Okay. So that's how collision is resolved in LTE using random back off. Now coming to NB-IoT, which is very similar to LTE, only changes it also supports 3.75 kilohertz subcarrier spacing. There the way the random access happens is slightly different. Instead of each user picking a sequence, here it does two things. Each user picks a sequence as well as a starting subcarrier. So unlike say LTE, which is an OFDM based system and all these sequences occupy multiple subcarriers, in NB-IoT, only the random access sequence always occupies a single subcarrier. So like for example, blue color is a UE here. So this UE started with the first subcarrier, but NB-IoT supports frequency hopping. So next, after some time, it jumps to second subcarrier, then it jumps to some eighth or ninth subcarrier, and so on. This hopping pattern is defined in the standard. So all you need to know is LTE uses all the subcarriers for sending the random access sequence. However, NB-IoT uses only one subcarrier at a given point in time to send the random access sequence. So now yesterday we discussed so much about IoT and broadband and so on, right? This is in line with that because LTE is about broadband. When they designed LTE, it was for broadband. That means users can support or process lot of subcarriers. That's why the sequence was designed like that. IoT, as we discussed yesterday, the data rate required is mostly very small and many IoT applications can be delay tolerant. So that's why they have picked only one subcarrier. Okay, but the same problem occurs if two users pick the same sequence and the same starting subcarrier, they will collide. Okay, and NB-IoT also uses, so there are only 48 possible starting subcarriers. So that means there are only 48 possible preambles in NB-IoT. Uh, are there any questions up to this point? Because we went off for some time. If anyone has any questions, please let me know. Uh, okay, otherwise I can just continue. Okay, let's move to slide 4. So if all this was grant free access, then what is grant based access? Then what is grant free access? As
Naveen,
the name says.
your slide is moving properly, so we don't need to
Okay.
advertise that. You go ahead with
Okay,
your.
fine. Sure, sure. So until now, what we discussed was grant based access. That is, base station tells where the UE has to transmit. Then what is grant free access? Obviously, base station does not tell. Previously, only the preamble was not told where to be sent. That is there in the standard where they have to send. So everyone sends at the same place. Now, data also they will send at the same place. That is what is the meaning of grant free access. So it's very simple. It's like Aloha, which you would have studied in computer communication networks or any basic course in computer networks. What is Aloha? To make it very simple, it's like whenever a user has data, send. That is Aloha. Okay. Slotted Aloha is slightly small variation over Aloha, which is whenever you have data to send, send it, but don't send it anywhere. You have some designated slots, send it at the beginning of each slot. That is slotted Aloha. Okay. Now grant free access is very similar to that. And why did anyone decide of doing grant free access suddenly? Like all these days we were doing grant based access, suddenly why pick grant free access? That is because, as I told you, with 5G, this revolution has started in supporting IoT devices. And for IoT devices, if I waste a lot of my time trying to only do message exchanging with the base station, get a grant, send again, and so on, it will be wasting time for the IoT device, also wasting power. So that is why people thought we can implement something like grant free access for IoT devices, where whenever they have data, they will send it. We will give them particular slots to send it, let them send it in those slots. Now, what is the biggest difficulty? As I have written here, it's easier said than done. It's very easy to tell like that. Even in this very small class of 40 people, if I say, whenever all of you have questions, ask it, and I give you just say 1 minute duration. If you have a question, you can ask exactly at 2:35, 2:36, 2:37, and so on. If someone has a question at 2:35, like if 5 people have a question, all 5 will ask the question at 2:35, because everyone wants their thing to be done first, right? I have a question up to this stage. So next immediate minute when I get a slot to ask my question, everyone will ask. So if 5 of you simultaneously ask the question, even if your questions are different, it will collide. Like I won't be as a receiver, I won't be able to separate you, even if you are different. Remember, okay? If your questions is exactly the same, then gone. Like I won't be able to separate you at all. I will be hearing that question somehow, but I would not know who asked that. Okay. So then we have to devise a scheme which can somehow separate users even though they interfere with each other, right? So all these years we were trying to mitigate interference, right? That was our whole aim when we designed networks: minimize interference, I will give orthogonal resources to you, and so on. Now suddenly with the introduction of IoT, you are actually encouraging interference, but what you are telling is I limit it, I'll encourage interference, but I limit it and somehow detect more users. Okay, so how do we do that in grant free forms the entire talk today. Okay, so how does base station recognize different users? What if two or more users transmit at the same time? And how can you simply send data? I mean, how will base station know this is even data? Like how will it know where are you putting your signature that I am this user and this is my data? Some signature has to be there, right? Otherwise, how will the user know whose data is where? So all these aspects we will discuss in this talk. Okay, before we go into details of grant free, let's revisit or let's convey why grant free is more useful than grant based. I told you just orally that the latency can be reduced. Here is a numerical comparison of the latency of a grant based system versus a grant free system. Okay, so various fields, I mean, see, this is not encapsulating every operation, but it's encapsulating most of the important operations. So see, this is called minimum waiting time for a service request. That is, you have sent your request to the base station that, hey, I want to send data. Base station has not yet told you where to send it. So typically, in an LTE system, you wait for 1 TTI. TTI means transmission time interval. Typically, it will be 1 millisecond in LTE. Okay, or it is just one OFDM symbol in 5G NR. So that's why I have written it in terms of TTI here. So one interval you have to wait. Okay, 1 unit of time you can think. That unit, how much time it spans can vary. In LTE it's 1 millisecond. In NR 5G it is one symbol which is around 70 microseconds. So there's a typo here. It's not 71 milliseconds. It's 71 microseconds. Okay. So in grant free, there is no need to wait. You just send. You wake up such that you wake up at your slot, at the designated slot, and send. So there is no wait time at all. See, then all this, see, UE has to send this service request on the control channel. E node B has to decode that service request. Then it has to schedule a grant. All these things are there, right? The entire procedure which I explained before, they take around 5 TTIs. And UE also has to process all these things. That will take another 3 TTIs. So totally 8 TTIs, they are not even applicable for grant free because you would have already sent your data. The moment you got your data, you would have sent it. Only time that will overlap is this data transmission time, which is roughly 1 TTI, let's say, and the decoding time of the base station. Data decoding time, that will not change. So you will incur latency only in these two fields. That's why you see that grant free can provide a faster access than grant based. However, I mean, there is nothing like free lunch in the world, right? Like if people are interested in machine learning, you can Google for this. There is something called no free lunch theorem also. Okay, so there is no free lunch in the world. Everything comes at a price. So this can reduce the latency, but what about the performance? There might be a hit in the performance. So we might have to build more complicated detectors in the base station, or we might have to live with a lower performance, as in very few users may get detected. Okay, so either complexity compromisation is required or performance compromise is required. Okay, but it reduces latency. Additionally, grant free also reduces signaling overhead. Okay, so typically, I mean, you need not worry about the numbers here. You just can look at the gains here. So compared to the original LTE preamble transmission, if we do grant free based kind of transmission, you can have up to 127% overhead reduction. Okay, I mean, you did not worry how this was all calculated. We plugged in some LTE numbers. I mean, I can say we because this reference one is part of my work only long ago. So a lot of overhead will reduce. So now what is signaling overhead? As I told you, control messages you have to send. Then base station also should send more control messages, and there will be some preamble to be transmitted. Base station has to account for overhead of that preamble transmission. Like this, multiple signaling overheads will be there just to establish the handshake between the base station and the mobile station. That itself will consume lot of resources, and that can be avoided significantly if you use grant free transmission. Okay, especially any control signal overhead can be reduced because you are not waiting for any control signal to send data. As and when you have data, you will send it. Now the last one is, and the most important thing is, it also reduces energy consumption. Okay, so here on the left side, PL means path loss. Okay, and RRC means the amount of time your radio is connected to the network. Okay, radio resource connection time. It can be 300 milliseconds or 100 milliseconds. We have evaluated two cases and two path losses, 144 dB and 135 dB. So this 4-step ratch is whatever is happening in LTE. Okay, so see, if you are having the 4-step ratch, that is control, preamble, everything, it incurs 19% of the power consumption goes there. 75% is consumed by data. However, if connection time is small, that is 100 milliseconds, 12% of the time goes in the ratch, 82% goes in data. Now look at this. Path loss is 135 dB. Data transmission will take only 36% of the time, but the ratch transmission will take 50% of the energy. Okay, depending on the path loss. So if your path loss is uh, if the say, I mean, here I think when they say path loss, it's kind of the received signal after path loss has been experienced. So if the received signal strength is lower, then you will end up doing the ratch procedure more number of times, because if your SNR is bad, then your preamble might not get through. Because preamble didn't get through, you will never get a chance to transmit your data, and so on. So that's why you will incur lot of energy consumption just trying to establish contact with the base station. Okay, now how will grant free work? Like if my SNR is bad, it is bad for grant free also, right? There is nothing like it's bad only for grant based. If I change my scheme to grant free, it becomes good. No, SNR is something defined by the environment. So if it's bad for grant based, it will definitely be bad for grant free. Okay, so then typically what people say is, don't do grant free for initial access. In initial access, you follow whatever your normal random access procedure that itself. But the moment you sleep and wake up, you remember we had discussed about this, when it sleeps and wakes up, still it decodes the PSSSS and still it goes requests for a connection if it wants to transmit data. There, when it is sleeping and waking up and it wants to send small data, at that time only you do grant free. So this was one proposal we put up, and I'm happy to say that when I was doing all this work, all this standardization was happening, and our industry partner presented this work to the 3GPP standards, and from that moment onwards, many companies pitched in, and everyone decided that grant free will be done for small data. Okay, that is, one initial connection is already established, but if you sleep, okay, if you sleep from the initial connection, and when you wake up and you have only a small data to send, then you do grant free. So that is why it's written in red here. Previously it was only idle connected. If you had small data also, you should do whatever you did in the connected mode. Now people are telling, if you want, grant free is still optional, by the way. They have not made it mandatory. If you want, for small data, you can do it in a grant free manner. That's what this entire state diagram is conveying. Don't worry too much about the finer details here. All you need to worry is this thing. If you have small data, keep doing grant free. If you have large data, go back to connected. Okay, go back to the original method. That's all it's telling. So this new state got introduced in the 5G standards for grant free. Okay, any doubts up to this point? Everyone has understood why we need grant free? Number one motivation is because we have IoT devices which have very small data, and we don't want to waste their energy consumption by making them wait to establish the connection. As long as they have data, send it as soon as possible. That's what we want to ensure. That is why we need grant free, especially for small data. And what is the drawback? We will have to build better receivers and we will have to do better detection. That is the summary up to this point. Okay.
Yeah, any question, participants, to if you want to clarify, you can clarify at this point before. Yeah, Venkatesh Kumar, I am enabling you. Yes, Venkatesh Kumar, you can go ahead.
Sir, good afternoon, sir. Suppose nowadays modern machines like washing machine or dishwasher, they are having home connect options. Using our mobile, we can, that is through IoT only.
Correct.
Suppose mobile is communicating with smart devices, that should be go through this grant free, or it will be using our GSM network and it will be possible.
Okay, actually, if you are talking, okay, maybe I should have demarked that. So basically, when we talk about all this grant free and the normal access, right, that is for cellular IoT. For indoor devices, they don't use cellular IoT. There is something called device to device communication. So they use device to device communication there. What I am talking about is all the normal wireless communication. If you want an example for such a thing, it might be like your say smart meter at your house, electricity meter, which will convey the meter reading every 15 minutes to a central server located somewhere at the center of your city or at one place in your city. All the homes in that city, they send their electricity readings to that central server. That kind of applications we are looking at. We are not looking at smart home sort of applications. They use a different sort of IoT altogether, which is called device to device IoT.
Thank you.
Yeah.
So Naveen, for example, if we have a, suppose I have a smart, for example, healthcare device, for example. So I have a wristwatch and it senses my BP. Suppose that if BP overshoots, it will send a message to my doctor. I have seen this kind of thing. So what is underlying framework for this? It is D2D?
Both. So in that case, there are two links, right? One is measuring power and giving it to you first, telling the reading to you first. That part will be D2D. But the moment it says it sends to doctor, so there are two links. The moment you say it sends to doctor, that will be cellular.
Okay.
So that second link is where we are trying to propose this grant free, actually.
Yes.
Okay. First link where the communication is in near distance, as in within your vicinity. That need not require cellular communication. That requires only D2D communication, device to device.
And
Which
okay,
can
if I'm not, yeah, yes, please.
Yeah, it can happen either through Bluetooth, infrared, or even Wi-Fi. It can happen through any of these technologies. But if you want to send a message to your doctor, then we assume that the doctor is far away from wherever you are residing. So that has to use the cellular link only.
Okay, yeah. And Naveen, one more question in the text box: how to differentiate the large and small amount of data? What is any thumb rule to keep the threshold?
I would have come to that. Yeah, that's a good question. So the thumb rule right now, again, there is no. These are all still being envisioned and still being researched upon. So typically, what people are telling is 32 bytes is your small data. Up to 32 bytes is your small data. Anything above 32 bytes is large data. So that in terms of size. Some people also like to define it in terms of data rate, because see, many people it's like this. No, it's like amount of bits does not matter. How fast I want to send it matters. So such people tell that instead of calling it as small data, large data, I'll call it as small data rate and large data rate. So those people say anything less than 50 kbps is small data rate and anything above 50 kbps is large data rate. This is some rule of thumb which people are using now. These may change as the networks progress. If for example we find out that even using grant free I can send 100 kbps very easily, then people will move it to 100 kbps. Okay.
Okay, thanks.
Yeah. Any more questions? Otherwise I can proceed.
No, I think no other questions, sir.
Okay, then I'll proceed. So what is transmitted in grant free access? That will be the question. No? So directly you are telling send data. Can we send data directly? Not really. Typically, right, there are two modes of transmission. One is called synchronous mode, where you have some sense of the base station timing, pretty accurate sense, let's say. You have pretty accurate sense of the base station timing. So you just put a long CP and send your data along with your pilots. Okay. Now, these pilots might be like your signature. So each user might use a different pilot sequence so that the base station knows when it sends acknowledgement, it says, hey, user 1, you used pilot type 1, I recognized you. User 5, you used pilot type 10, I recognized you. So that way base station can send the response. Okay. The pilot can be your signature. There is something called asynchronous mode where you don't know the timing of the base station very accurately. You may know it at a very coarse level. Maybe you are off by almost say 40 samples or even 50 samples sometime. You just know it in a very crude manner. Okay. Then you will send something called a preamble followed by the data. Okay. So remember in the old LTE or NB-IoT, you would first send preamble, wait for that to be recognized and then send data after base station recognizes the preamble. Now what you will do is you will send both of them together. And this preamble will not be same as the LTE preamble. This is some new preamble you will build for yourself. Okay. So both these kinds of grant free access methods exist. Today I'll mostly discuss about the second mode, which is the asynchronous mode, which is more prevalent because as I told you yesterday, the clocks used in IoT devices, they are not very costly clocks. Okay, you want to make these devices cheap. So you will put a very cheap crystal in it, because of which the deviation will be large. And since the deviation will be large, your center deviation from the center sampling frequency will also be large, and that affects your timing offset, frequency offset, everything. So we can safely assume that you are off by 40 to 50 samples, and that's why you have to go for asynchronous mode. So that's why I'll be discussing more on the asynchronous mode. And it among these two modes, this is the tougher one. If you can solve this problem, you can replace the preamble with a long CP and solve that problem very easily. Okay. And as I told before, the main challenges are minimizing collisions. What if two users pick the same preamble? It will collide. And how to do multi-user detection. These are the main challenges. Okay. So this will be little dense. Next 4 slides. Basically, we are trying to summarize all the literature that has happened. Okay. I think Zoom may also still work. So I'll just try to zoom to few things. Um, First thing is basically what people have done. That's what we have to look at. See, grant free, since I told it's very similar to random access and Aloha, there are a lot of works in these things. So what people try to do is, anyway 5G was giving massive MIMO, can we do grant free with massive MIMO? That is, somehow I'll just do normal kind of random access, okay, very similar to LTE kind of access, not in 2 steps, not in 4 steps, but I'll reduce the number of steps. So this was the conventional LTE 4 steps, which I already showed you. People thought we will just do 2 steps, which is like I'll send data plus preamble, then base station will send, okay, I found both data and preamble. Such easy 2 step. This is what I was telling from before, only 2 step. So people try to attempt this in 5G. They found that if I have only one antenna at the base station or only two antennas at the base station, it's very difficult to do any detection. Okay. But they didn't do a lot of rigorous analysis on it. They just thought with little antennas, it may be able to difficult to detect these things. So I will use massive MIMO and detect them. So that's why they resorted to this, what we call as a 2-step procedure. And they evaluated that has been presented as technical reports and so on, telling that, yeah, this 2-step is possible as long as you have massive MIMO. Okay. Now the question comes, not everybody will have massive MIMO. See, when these people evaluated it, they took a large number of antennas, 64 antennas, 128 antennas and all. But people are right now slowly introducing 5G. Maybe they will start with 16 antennas, 32, maybe 5 years down the lane, they will have 64 or 128. So again, the question came, then I'll have to somehow get this detection done, not in massive MIMO, but in some other scenarios also. Okay. So this is a very recent paper, this 4, not from our group, but another parallel group in UK. So they tried to find out whether they can do grant free access for small data without massive MIMO assumption. And they were partly successful. They found that at least they did a good detailed study of what gives them the lowest energy consumption. And obviously, the 2-step procedure, which is only this 2-step A procedure, gives the lowest energy consumption. The line which is at the lowest place is the 2-step procedure. Okay. Slightly more energy consumption was this 2-step B procedure, where something may not get detected at the first attempt, but it may get detected at the second attempt. So I'll give you these slides, so no need to worry too much. So it sends a message. It didn't get the data, completely didn't get detected. So it will retransmit the data, and that time it got detected. So it's like first time it was a failure, second time it was a success. Such a method consumes slightly more energy. Other things like NR supports something called early data transmission. As soon as you get the preamble's response, don't wait for the grant, send the data itself. That was worse than this one, and the original LTE's 4-step was the most worst. Don't worry about dotted lines, only look at the solid lines. Dotted lines is an inferior receiver. Solid lines is a better receiver, which will handle more interference. So as expected, LTE's 4-step patch was most energy consuming, followed by current. NR has something called early data transmission. That is, as soon as the preamble is detected, don't wait for the grant from the base station. Base station will give you some fake grant or a temporary grant. Use the temporary grant and transmit. So that was the second worst. But whatever we were discussing as grant free, right, those come in the lowest energy consumption. So this was a very, very good study, because finally they told you need not rely on massive MIMO. You can do normal procedures. If you build a good enough interference robust receiver, you will be able to detect grant free transmissions. But remember again, grant free access for small data. If I increase the data size, this will also fail. Okay. That is the whole summary of performance of grant free schemes. Then people also looked at this entire grant free from another way. So instead of telling small data, massive MIMO or anything like that, people thought I will look at this problem as a collision resolution problem, because from a long time we have been resolving collisions, right? Especially WLAN and all, you have very nice collision resolution protocols. So people thought we will look at it from that angle, let people transmit in a grant-free manner, I will look at it as though two users are transmitting at the same time, and I have to find out a collision avoidance or a collision resolution protocol. And they approached that using different probabilistic models, and they were able to reduce the collision probability to some extent. And they were also able to find out if there are X users per slot, then I can minimize collision. If there are more than X, I can't minimize collision. Some numbers like that. I don't want to spell out the numbers because this is an ongoing field of research, and today if somebody has done it as 8, like I will be striving hard to make it 10. So the state of the art would be, I think, around 10 as of now. Our research is now trying to push it to 15 or 18. So it's like a competition, small competition going on as how many more users I can support with a given collision probability. So that was one more way of looking at it. And people also built, remember pilots can act like your signatures. So people tried to build some non-orthogonal pilots so that it will help in designing pilot sequences easily and also help in detection. Also people tried to do some spread out the traffic. So typically what happens if there is an IoT device, it's like this. Whenever somebody configures a smart meter, right? I mean, it may sound very dumb, but this is what is actually happening. If you all buy smart meters and let's say they are all supporting the, they are all reporting the result to the government electricity server. Okay. Most of these guys, they will put say 500 smart meters in an area, they will configure it at the same time because there is an option there to change the time, but they will just buy it from the vendor and put it, right? So all of them are operating at the default time. So all of them will try to send the result at the same time. So these are like, because people don't know about the intricate things which are happening. So when there is something called a start time or an init time, okay, that should be changed randomly for each device before they install the smart meter. But unfortunately, they don't see all that. I mean, we can't blame them also. Government has given some device, they put it there. That's it. Okay. So they don't change the start time, and all the 500 meters in that area, right? They all start reporting their electricity readings at the same time. Which now if they are doing orthogonal access, each one will go orthogonally and all. But if for example we change to grant free access, it will be a havoc there. Okay. So that's why what people thought was, let's spread out the traffic. That's what researchers were thinking. Instead of concentrating traffic over in a one burst, we will spread the traffic over multiple bursts. And that was what is this sporadic traffic kind of thing. Sometimes you have traffic, sometimes you don't have traffic. When you have traffic, spread it and so on. Lastly, build more advanced receivers. So I was grateful to be a part of this team. This is a collaboration I'm continuing with my PhD supervisor. There, one of the visiting students, he built a different receiver called a widely linear receiver, which is able to separate more users than a normal receiver. Okay. However, see, everything comes with an asterisk mark. Okay. Such receivers can work only for real valued modulation. That is, it can work for BPSK, 4PAM, 8PAM. As long as your modulation scheme is on one axis, it works very well. If I take it to complex modulation schemes, it will suffer. Okay. But still, it's a good way forward because as I know, IoT may not require very high data, so I can work with BPSK itself most of the time. Okay. So this was another thought process. So now you got two thought process for grant free. One was introduce more antennas, make it closer to massive MIMO system, improve the performance. Second one is see it like a collision resolution problem and improve the performance. Okay. So these are, see, collision avoidance scheme and a power domain NOMA scheme. So PDMA is power domain multiple access. So you are separating two users in power domain. So here they are seeing how the throughput is affected based on the total traffic. Okay. So depending on the total traffic, which will give you a very good performance. So see, normal slotted aloha will not give you, that is the one in green, normal slotted aloha. We know, right? Slotted aloha takes the maximum will be 36%. We might remember from our undergrad days. So that's it. 36% of the throughput is what you will get. It may improve radically if you use some NOMA, non-orthogonal multiple access techniques, or you use some collision avoidance schemes and so on. Okay. So one representative result I am putting it here. This is not from my work, but you will know that these are all the different works in grant free. Okay, so this was the second approach, which is trying to avoid collision. Now let's go to the third approach. So four approaches are there. I'll finish all the four and then we can take questions. So third approach is, as I told you, most of the grant free will be for asynchronous because your clocks will be bad and your drift will be large. So asynchronous requires preamble design. The third approach was, I'll minimize collision by designing very nice preambles. So what do you mean by very nice preambles? That means if two preambles interfere with each other, it should cause minimal damage. That is, it should have very good cross correlation properties. I correlate with the first preamble, I should be able to, the effect of the second preamble should go as close to zero as possible. So like that, I have to design the preambles. So again, people first thought, first let me design such preambles for massive MIMO scenarios. So they took massive MIMO, they put grant free there and also designed better preambles. They had a very good success with it. Then people went to the extent of deriving the optimal preamble length, that is the number of samples your preamble should contain, so that it performs very well. Okay, and that is what is given in the graph here. And of course, see, that is based on the number of antennas. Okay, see, as you increase more and more antennas, that's why this arrow mark is there downward. If I increase more and more antennas, I need shorter and shorter preambles to achieve the same result, same performance. But one amazing result is the preamble length for grant free is always higher than the preamble length for grant based. See, black is all grant based and red is all grant free. The preamble length required for grant free is always more, right? Because there is more interference here. In grant based, there is less interference, but what is more in grant based? Delay is more. Here, delay is less. That's why I told somewhere you have to compromise. So you will have to end up sending a slightly longer length preamble, but your data can get sent very quickly because you are using a very good preamble and so on. Okay. Then many researchers tried with non-orthogonal sequences and again grouping preambles, grouping the beams. Like this, they have tried multiple methods, but the summary is this. At the end of the day, grant free requires a longer preamble than grant based, but still it saves time because the user is not waiting to send their data. They send the preamble followed by data. So that is the main takeaway from this approach. Okay. Then the last one is the most well-known thing. It's typical of our teachers, especially. Whenever a student doesn't understand something, what do? We repeat. He doesn't understand again, what do? We repeat again. Right? But again, we also have a bound, right? You will repeat it probably 4 times, 5 times. Then you will say, okay, I have repeated 5 times now. If you still have this question, meet me outside the class. We will resolve it. So that things progress. Whatever we have in our buffer progresses. So same thing. People try to incorporate repetitions. Don't send only one preamble and data. Send 2 preambles and then send same data but multiplied with 2 different preambles. One of them may get detected at the base station. Good, as long as base station detects one of them, it's enough for me. So like that, researchers wanted to incorporate repetitions. Okay, and of course retransmission. Retransmission is even after I sent some 2-3 repetitions, still you didn't get my data, I will retransmit again, like that. Okay, so again, many people tried it for massive MIMO. They even tried it for NB-IoT with orthogonal preambles itself initially, and that is the result which I have put here. Okay, and they have it is very clear that if you have repetition, the probability that you detect will definitely increase compared to when there is no repetition. Okay, so repetition and retransmission is another standard way of improving the performance. But again, you will pay a small price. Performance will improve, but with every repetition, you are increasing the delay. Remember, with every repetition or with every retransmission, you are increasing the delay by some amount. Okay, so these are the 4 main approaches. Our research has also been in one of these 4 approaches only. So next I'll continue with what we have done so that you will get a better idea what is the problem we are trying to solve. Any questions up to this point? This is the general structure of grant free.
So any questions from the participant side? Okay, no flags, Ravi. We can go ahead.
Yeah. So we'll go ahead. So what we were trying to do is this. It's a very simple problem. Everybody can understand. There is nothing too complicated in this. Okay. So we tried to consider an asynchronous grant-free system, as I told you before, which has a preamble followed by data. We consider the following three events in the system. First event is all users in a category are successful. Okay. So if there are 10 users coming to the network, all 10 are successful. Second one is all but 2 users are successful. That means if there are 10 users coming to the system, only 8 are successful. Exactly 8 are successful. 2 are failing. Third event is at least all but 2 users, which is slightly better. That is at least 8 are successful. So it can be 8, 9 or 10 if 10 users are coming to the system. Now, how many users are coming to the system? We have two categories. One is called fixed, that is, there is always a fixed number of users. Second one is a random category. The number of users coming to the system might be random. Okay. So now I have a very small question. Typically, when you are modeling number of users or number of packets coming to a Wi-Fi access point, using what distribution will you model? Number of packets. Can anybody attempt? Typically, with what distribution will you model?
Any guess from the participants?
Yeah. Okay. One hint is number of packets cannot be negative. Worst case, it can be 0. So you cannot tell Gaussian because Gaussian will have both negative and positive, right? So what we may use to model number of packets arriving at a router?
Those who are working in this kind of queuing theory, you might know.
Yeah. Okay. Typically, we use something called a Poisson distribution. Have you heard of Poisson distribution? You can Google for it. Poisson. It's basically a limiting case of a binomial distribution. Okay. So if you want to really simplify your model, you can use uniform distribution. That is telling probability that 0 packets come, 1 packet comes, 2 packet comes are all same. But that is not a realistic model. But typically for traffic number of packets and all, people use Poisson distribution. So that is what even we used. Whenever the number of users are fixed, there is a constant number of users. And when it is random, the randomness is characterized using a Poisson distribution. Okay. So now again, don't get scared with the math. Since I am sharing the entire screen, I think even my notes should become visible. Is this note visible? Like a blank page, did it come?
Yes.
Okay. So I will use this note once in a while because we just have to come up with these small expressions once in a while. So this is the probability that all users are successful. Event 1 is all of them are successful, right? So if there are m users here and there are n preambles, when are all of them successful? This is a high school problem, believe me, because it's like this. For m users, I can draw m blocks like this. First user, second user, up to mth user. When will all of them be successful? When all of them pick a different preamble. Now let's not worry too much about data. We will talk about preamble success. So we will say when two users pick the same preamble, they collide. So they are not successful. Everyone has to pick different preambles in order to be successful. That's very easy, right? So how many choices we have? First guy has n choices. Second guy will have n minus 1 choices because he cannot pick the same preamble which the first guy picked. Third guy will have n minus 2 choices. Like this, the mth guy will have some n minus m plus 1 choices, right? N minus of m minus 1 basically. So this is the number of choices they have. If I didn't put any such restriction, each one would have had n choices. So this is my sample space. all possible choices. So that would be n to the power m. The product of this, because choice of each person is independent, product of this would be my actual numbers of ways in which all have picked different preambles. So now what is the probability? It's just this product up to n minus m plus 1 divided by n to the power m. This is my probability. It's only in a fancy way we have written this way as a factorial. That's all. There is nothing big. See, n factorial by n minus m factorial, that will give me that product into 1 by n to the power m. So see, nothing big. There is no need to get scared with any math. It's a simple high school problem, as when everyone picks a different preamble, they are successful. Great. Now, why? Now I have an expression, my problem is solved, I'll think. But the problem is this, right? Once you have such ugly factorials in your expression, you have no way to simplify them further. So what we will do, we'll end up finding some lower bound for this and an upper bound for this. Surprisingly, people had not found this. Okay, it's just sheer luck. We tried to find, of course, I am also a slave of Google sometimes. I feel this expression people know from ages, so some bound should have been found. Surprisingly, no such bound was found. So we found one lower bound for this and an upper bound for this. Okay, so what it means, this real one, on the left side we lower bounded it by something, and here we upper bounded it by another thing. Okay, and we also proved that these are tight and so on. I'll not go into those proofs. So we had a very tight lower bound. Okay, so now if my lower bound probability itself is 0.9, let's say, that means 90% of the time people are successful. 90% of the time all users are successful. If lower bound itself is 90% successful, then in the real probability it will be slightly above 0.9, because this number is above this number, is slightly above 0.9. So that's why we kept on using only the lower bound for the remaining analysis. Okay, so we just started using the lower bound, and using this lower bound for a given number of users m, you can always find out the number of preambles required such that some probability of success you can ensure. So that probability of success is this PLB, 90%. So we have also used 90% as a number. Okay, so that's how we found the number of preambles required when number of users arriving is fixed. Okay, then there is another way to look at this problem. All users being successful, finally this was the probability we arrived at, right? Another way to look at this is strict probability kind of way. Like, first I will find out individual user success probability, then I extend it to all user success probability. Individual user success probability is even more easy than this. So again, just see, one part I'll explain in detail like this, remaining parts you can derive later. So individual user success probability is basically like this. First user, second user, let's say again m users are there. I give this guy picked one preamble. Okay, he picked something. Now, as long as these guys pick something different other than him, I'm just looking at one user now. Okay, I'm not looking at all users being successful. One user is successful if he picked a preamble different from all others, right? Then he will not collide with anyone. Agree? So without loss of generality, let's say this guy picked preamble number 1. So he picked preamble number 1. So all these other guys, they can pick any preamble between 2 to n. Let them collide. He doesn't care. He will be successful. These guys can pick anything between 2 to n. So how many choices each of these guys have? Each one has n minus 1 choices, right? 2 to n. So n minus 1 choices. So like this, all of them have n minus 1 choices. So n minus 1 whole to the power m will be the total count. Of course, if I didn't impose this condition, the sample space would have been n, which is n to the power m. So this probability will be n minus 1 by n whole to the power m minus 1, sorry, because there are m minus 1 users here. First user has already picked something, which is 1 minus 1 by n whole to the power m minus 1. This is one user's success probability. See how much time it took? Looks complicated or looks like some exponential expression and all. It takes literally 2 minutes to derive it. So now this is the individual user success. Now we will say each user is independent. So if there are m users, then the success rate of all m users will be raise this to the power m. So if I have 2 users, it will become p squared, p cubed, and so on, right? So all users are successful. With probability, this thing raised to m. So m into m minus 1, right? This should be the probability. But see what I have written? We have m by 2 there. There is one division by 2 there. We have made it p to the power m by 2, not m. Why do you think so? The answer is very simple. If someone collides or if someone picks a preamble same as the other user, that means both are dead. That is, both will collide, right? At least 2 people will collide. So if one user fails, it implies always that at least one more user has failed. So I need not raise it to the power m now. I can only raise it to the power m by 2, because if one fails, definitely one more fails. So in terms of pairs, m by m users, if I have to consider them in pairs, I have only m by 2 pairs. So I need to raise it to the power m by 2. That one small trick we did and we got much better results. Okay. We also proved that, see, remember, this is also all user success probability. What I had in my previous slide, this equation 2, this is also all user success probability. We also proved that these two are very close to each other. The expressions are very close to each other. So those are more intricate proofs, so I am not doing it here. So finally, we have some proof as given the number of users, given the number of preambles, this is my success probability. Or given a success probability, I can find out the number of preambles required. So these are some small things we derived. Then we extended the same for random, that is Poisson distributed. So there, because they are all random variables, we can't find out the exact probability. We can find the average probability of success. Average probability of success of all users we found out. Similarly, average probability of success of a single user also we found out. Okay. So just to give a hint, I will not sit and simplify. It will take little time. So anything, we always remember this expected value definition. Expected value of x is summation over all x times px of x, where this is the, for a discrete random variable, it's the PMF, probability mass function. Okay. So in the case of Poisson, Poisson is also a discrete random variable. This PMF is of the form e to the power minus lambda, lambda to the power k by k factorial. Again, this you would have seen in Aloha, computer networks, and so on. Okay. And now x I know is my entity, right? It's the probability of success, which I know from my previous thing, that n factorial by n minus m factorial, all those things are there, right? So instead of this, I'll have my probability of success, which was given by that n factorial by n minus m factorial times 1 by n to the power m. That I'll multiply with this, take summation. It will easily simplify. It looks like this, but it will easily simplify. And finally, you will simplify it to this form. Okay. Now again, I have an expression for the probability of success of all users. Okay. Using which, if I set this to 0.9, I can always find out the number of preambles required for lambda users. Lambda is the mean number of users coming in. Okay. So I can always find out the number of preambles required. Same, whatever I did for fixed, again I can repeat for Poisson. I can find out the individual user success probability, then raise that to the power lambda by 2 and get the all user success probability. Okay. So this and this equation 5 are also very close to each other. Again, we can prove that very easily. This and that equation 5 are very close to each other because they represent the same entity. It's just a different expression. Okay. So what we ended up doing for a given grant-free system, we found out if all users have to be successful, this is the number of preambles you need given these many users are occupying the network. Okay. So these are our results. See, as I make that probability more and more, the number of preambles n that I need obviously increases, right? And look at the shape of the curve, it's increasing exponentially. So look at this small example. Let's take, like, see, m is the number of users, okay? And these are fixed number of users. This is in the random case. Left side one is the fixed number of users. Say 80%, which is 0.8. 0.8 requires only 200 preambles. That is, if 10 users are coming and they have to be successful 80% of the time, all have to be successful 80% of the time, that takes only 200 preambles. But if they have to be successful, say 90% of the time, it changes to 400 almost. You need 400 preambles. It's like double. The probability didn't even change by a huge factor. 80% changed to 90%, but the number of preambles required almost doubled. So the number of preambles increases exponentially. Okay. Same thing we observed even when the number of users were Poisson distributed. So what we thought, okay, now if I increase, so typically what they say is you want lot of people to be successful, and what the current networks are designed for is for 99% of the people to be successful. That is, all users have to be successful 99% of the time. Okay, that is what current networks are designed for. So if I take that, with only 10 users, you require 4,482 preambles. So what we told, let's relax this condition. Let's say instead of 99% of all users being successful, like all users being successful 99% of the time, let's allow at least 2 users to fail. I mean, at most 2 users to fail. Okay, allow some users to fail, but we'll cap them at 2. So that if we consider, and if we set that to 99%, that is 99% of the time, all but 2 users are successful. At least all but 2 users are successful. That is, if you have 10 users, 99% of the time, 8, 9 or 10 are successful. Okay, exactly 10 are not successful, but 8, 9 or 10 are successful. If you just make that small change in your design, then the number of preambles required reduces from 4,482 to just 278. It's a huge 93% reduction in the number of preambles. Now everyone will jump, right? Like, oh yeah, you reduce the number of preambles, but now 2 users will collide. Every time, many times 2 users will collide. Fine. What I will do is I'll create a separate window and I'll make the 2 users retransmit only in that window. That's how we solved the problem. So we created a separate window for failing users when they failed the first time, and in that window only failed users will transmit. No new users will transmit. So it increased the number of resources little bit, but it hugely reduced the number of preambles. And again, same behavior was observed even in the Poisson case. Okay, so this was the initial work. All of this got published in a conference paper. This was all the initial work. So in our next work for the journal paper, we considered all these works along with repetition and retransmission. Okay. So remember one thing about failed users. If a person fails now, he will definitely retransmit in the next time, right? And if he fails there, he'll again retransmit. So now even in the present networks, new users and retransmitting users are sharing the same resources. Even in the current LTE, 5G, all networks, new users and retransmitting users, they try to obtain access at the same place. Okay, what we told was, let's not do that because it will create something called a snowball effect. Because if you have more and more retransmitting users, they will add to the current set of users, right? So that number will keep on increasing. The network load will become very high very soon. So what we told, let's not do that. Let's treat retransmission like failed users separately. So I always just give example of my class here. If there is a weak student, give him extra attention. Don't put him along with other students. So give that extra attention to failing users. Give them separate resources to retransmit. Give them specific attention. Give them better power. Give them lower code rate. They might also become successful immediately. However, there is a limitation, right? I can't afford to have too many failed users. That's where our conference work came into picture. No, don't worry, we'll not have too many failed users. We'll cap it to only 2 users. So you will have to give this special requirement only for 2 users, not more. So we adopted that strategy and we were able to have a lot of success because for retransmitting users, we avoided this snowball effect altogether. Okay. So see, this is what happens basically if I do more and more repetition. I told you, right, with repetition, number of failed users will reduce. So this is, remember, this is not even average. Okay, green is the average and this blue is max. So this is the original approach where they were designing for 99% all 10 users have to be successful. We designed for 99%, at least 8 should be successful. When we did that without repetition, number of failed users increased to 4. Though we wanted to limit to 2, many times it was 2, average is still 2, but occasionally max number of users went to 4. But the moment we introduced one repetition, see, the number of failed users got capped to 2. And with more and more repetitions, number of failed users got capped to 1, which is same as the conventional method. Then we told, see, our method is superior because if you use our method with repetition, we give you same performance as conventional method, and we also consume very little preambles compared to others. Okay, same was observed when you have 20 users arriving, 30 users arriving, even in the case of Poisson, same thing was observed. If you have repetition, even with just one repetition, we were doing lot of good work compared to the conventional algorithms. Okay, I think in the next few slides, there is little more math of this repetition due to time crunch. I will skip it, I think, but this is again very easy. Only first one I'll explain, maybe retransmission I'll skip. Repetition is very easy to understand. So see, now what is the probability of success of an individual user after k repetitions? Very standard. I think this is like a third sem or a fifth sem probability problem, because when will someone get succeeded after k attempts? That is the same question. First I have to find out what is the failure. So these are k attempts, let's say first attempt, second attempt, up to k attempts. What is the probability of failure here? If the probability of success is p, probability of failure is 1 minus p. Here also probability of failure is 1 minus p, and so on, right? So total probability of failure will be 1 minus p whole to the power k. Therefore, the probability of success after k retransmissions will be 1 minus of 1 minus p whole to the power k for a given user, right? Now this p is an ugly expression which we derived, this 1 minus 1 by n whole to the power m minus 1 individual users p. So that's why it became like 1 minus of 1 minus 1 by n whole to the power m minus 1. This entire thing, you raise it to k and 1 minus that. It looks like this when I write it, but at the end of the day, that's very simple expression. See, that's what I have here. Okay, same thing, probability of success of all users now. Now, with repetition, I can't do that m by 2 pairing, because after 2 people repeat 2 times, one may become successful, another may still fail. Okay, so that m by 2 pairing I can't do, so I have to raise it to the power m. This thing I have to raise it to the power m. Same thing for Poisson. That's it. So we were able to derive these simple expressions. That was the whole point of the paper. People were doing lot of complicated things to do, grant free, probability, preamble analysis, that, this, and so on. We told, like, with very, very basic probability tools, you can get very good expressions completely modeling the grant free scenario. That was the main contribution of this paper. Similarly, you can do for retransmission. This math is a little bit intricate, so I'll not go into the details here. Okay, so this math is, it will be a little more complicated than repetition. So you can assume that this is derived correctly and we got some result with retransmission also. So when I explain the results, you will understand. See, so this was the success we got, the results we got for probability of success of all users in the bottom graph and per user success probability we have derived both the expressions, right? First thing is analytical and simulated are matching almost to the 6th decimal. Okay, we ran all the simulations in MATLAB over 10 to the power 6 iterations, and for retransmitting users, we had only 12 preambles. They could pick only one of the 12 preambles. For others, we used more preambles. See, as you know, here we have given, right? We use 64, 308, 120, 1289 or 2944. But when somebody is retransmitting, they always pick one out of 12 preambles. And we also assume that you may have sent, but you may not get the ACK. That may happen 0.1% of the time, which is again a very standard assumption which they make in literature. So, and we consider probability of all users being successful is 0.9. We try to reach that number. So see, with 64, easily we will reach that number only for a very small number of users, around 4 users with 64 preambles. Why is 64 there? Remember, LTE uses only 64 preambles. So with the kind of requirement of grant free, if I use LTE, I can only support 4 users. Okay, which is very bad, because I want to support massive number of devices and all in IoT, right? So there is no other option than increasing the number of preambles. So we showed that if you have like around 1000 preambles, you can easily support like 1289 preambles. You can easily support around 15 users. Okay, people have done lot of massive MIMO things and all and increased from 10 to 12. So we just told increase the number of preambles and you will be able to support more. Our next paper we are working on how to increase those preambles. I mean, that is slightly more difficult problem. We have solved it, but it takes more time to give established results. So this was more like a overview, like proved that you increase it by this much. I don't know how you will do it, but if you increase it by this much, you can support more users. Okay, same sorts of results we observed even in Poisson case. Okay, like with around 475 preambles, you can easily support 10 users. In just to give you an example, in massive MIMO they needed 64 antennas to support 10 users. These are all for single antenna base station. Single antenna base station, instead of having say 64 preambles, you make it 475 preambles, you will be able to support more users in a grant free manner. That's what we proved. Okay, so these are some more scenarios. These numbers are there for me to show you that, see, they are matching very closely. And remember, all our analysis is on lower bound, so simulation will be better than the analytical, because for our analysis we have used the lower bound of the probability. In reality, if I set it to 0.9, in reality it will be actually 0.903, 904 and all. So every time the simulation is always better than the actual analytical result we have. Okay, see, in fact, simulation here predicts in the last case 0.99995, but analytical predicts like that, but in simulation it's like everyone is successful. So that way we were able to show that we can have accurate analytical expressions to find out the success rate of a grant free system, and to almost the 6th decimal and all in many places. And also simple tricks like increasing the number of preambles is sufficient. Don't worry too much about number of antennas, just increase the number of preambles. That is what we tried to convey. Okay, and now this is the last one, which is the trade-off with respect to repetition and retransmissions. Okay, so here K is the number of repetitions, L is the number of retransmissions. So repetitions happen together. At a time you will send so many repetitions. Retransmission is you wait, base station didn't send you something, so you retransmitted. So somebody will ask, right, one repetition, is it enough? I will do 2 retransmissions. I am fine with it. How does it impact? So K1, L1 means 1 repetition, 1 retransmission, 1 repetition, 2 retransmissions, and so on. Like that, if we do, basically, finally we find out that 2 repetitions, 2 retransmissions will give you like 0.999 probability. See, this 3 nines and 5 nines are very important numbers in 5G, because this 3 nines is the success probability required for MMTC applications, that is 0.999, and 5 nines is what is required for URLLC applications, ultra reliable low latency communication. So we see that 2 repetitions and 2 retransmissions are enough to do MMTC. If you add one more retransmission, that is enough to do URLLC. That is with 64 preambles. Okay. If you increase the number of preambles, 3 repetitions and 1 retransmission is enough. 3 and 2 is more than enough for URLLC. Now that is the thing. If I look at the energy consumed, right? The energy consumed for this and this will be basically 374 and 564. But the energy consumed for this and this will be 244 and 494 millijoules. So it's like you are comparing 244 with 374, 494 with 564. So it's a huge reduction in the energy consumption, right? Even in terms of latency, see 8 versus 16, 18 versus 25. So we showed that increasing the number of preambles will also reduce the latency, will also reduce the energy consumption, and will meet your requirement of 0.999 and 0.59s. Basically, it will meet lot of applications. Okay, so very simple. It was, I mean, for me also this was really an eye opener, because we always think research means there will be complicated models, there will be complicated ways to derive things. It was almost like my PhD student, and there was one more undergrad student. Maybe because of them I had to go some in a very simple way, especially with the undergrad student, because all he knew was just basics of probability. So he was trying to look at everything as basics of probability, which actually helped me, because if it was given to me, I would have modeled it as some stochastic model, something big, and tried to analyze. He was forcing me to analyze it like basic probability, and we finally were able to do a lot of analysis like that and show that grant free systems are feasible. All you need to do is increase the number of preambles. Okay, so that's the last slide. How do you generate that preambles? Great, you did all the research, you showed increase the number of preambles. How do you do it? This is still ongoing. We are exploring few sequences, orthogonal sequences, quasi-orthogonal like Zadov-Chu, Gaussian sequences, Gole sequences. We are trying to explore different sequences and find out if we can actually generate 475 preambles very easily. Okay, so that is what we are at as of now. The whole purpose of this talk was to introduce you to grant free and to convince you that if you know your basics well, very good research results are possible. Okay, you need not require very high-end tools to do good research. All you need to have is a good set of eyes to look at problems in a simplified way, and students who are working very hard and yourself working dedicated towards that problem. Respect whatever small ideas your students give or you yourself give. Okay, you yourself come up with. Don't dismiss any idea as stupid just because it's simple. Lot many times simple things will give you amazing results. This was one of those instances where very simple things gave us very good results. Okay, so with that I would like to conclude my talk. So these are all different papers in grant free using which I have summarized the slides. That's it. I know this was very different from my first session. First session was kind of an overview thing. This is more of an in-depth thing, but I hope by now you have got some idea of grant free access. So if you have any questions, please go ahead and ask me. So no questions. Yesterday you people had a lot of questions, right? Because that was more basic compared to this.
Yeah. Yeah.
So the main takeaway is this, that's all. You need not wait for a grant from the base station. Whenever you have data, you send. But if you do that, you will collide. So you need to build better receivers. Or you analyze how much collision I will experience. That's all. That's the main idea.
Yeah, some of the scholars are here. They too email me about the slides and other thing. Yeah, one of the participant is asking for your yesterday lecture recording. Already I have posted in the Teams. You can get access to that. So yesterday Naveen's lecture, today's slides, everything is there. So there is one question from the participants, Naveen. So the test beds are validating these results.
These are not physical layer results. These are MAC layer results. So if you say test bed, basically I'm trying to incorporate a traffic pattern which is close to real scenarios like that. So that is my test bed. What you asked, if you are specific about physical layer, like yesterday, this has to go on some subcarrier and all, that research is ongoing. There also we have obtained some good results, but we are still in initial stage, not at a publishing stage. So we are slowly working towards that solution.
So Naveen, are you developing separately for your institute or in collaboration with the Madras, that IIT Madras team and Hyderabad team?
No. This is ours, separately ours.
Oh, I see. Okay.
Yeah. So once I actually, it's like this. Like we want to do this and. So the plan is to collaborate after we demonstrate some small say success from our side.
Okay. Yeah. Okay. Any other questions, participants?
So one thing is that all these are compliant with 5G, 4G, 5G, the kind of solutions we are developing. They can be readily adopted in 4G and 5G. That's what I was saying. Honestly, there is no concept here other than third sem or fifth sem probability. there is nothing beyond that we have used actually.
Yes. In fact, whatever you have used today in the math is very, very basic, except these Poisson distribution, interarrival time, these things we have studied in an undergrad too.
Yeah. So only that. I mean, we just use the math looks a bit ugly when you simplify, but core tool is very, very simple. Anyway, I think once they revisit it or try to do it themselves, they will also feel. So there's a normal tendency that people tend to see equations and simply skip over it when they read papers. So that will change with the time. Once they understand that it's a simple equation, it will change. So any other questions on LTE 5G also I can take, forget grant free as such. Any other questions remaining from the last session or any general question you have about 5G implementation, 4G implementation? We have 10 minutes, so I can take that.
Yeah, I was also planning to conduct me a kind of a 1 day or 2 day short course. I will get back to you sometime.
Yeah, sure.
Maybe in the like a winter school or mid-semester break, I'm planning something. So just maybe a 2 day specific workshop for this LTE and broadband technologies and 5G NR.
Yeah, sure.
We'll get
See,
in touch.
interestingly, your name shows up as NR in Microsoft Teams.
Okay.
Yeah. So yeah, we can definitely have it. I mean, we can open it to both IIT Dharwad and Goa. And
yeah. I am just instead of like an open FD, I was trying to make very specific and target audience.
True. Even we are on some of those lines, so jointly we can come up with something that is also fine.
Yeah.
Because all these, even machine learning is a big thing, right? So everyone wants to know how is machine learning applied inside 5G and all.
Yeah.
But I usually take it up as a different topic. I don't merge it with the standards. Because very few people are doing machine learning for standard related things. They do it for their own proprietary 5G or 4G solution.
But do you have any tie-up with a particular industry that which might help you to establish the lab, or you connect the pieces separate together and then integrate them?
Yeah, that we don't have any industry as such. We use these MATLAB toolboxes only. One project I have where we do have an industry partner. My imprint project, it is with Lekha Wireless. They are a small company in
Okay.
Bangalore.
Yes.
Yeah.
Bangalore. Yeah.
Yeah, so it has a lot of my ex-colleagues also, like those who were with me in Tata Elxsi Broadcom. So
Yes.
yeah, so we are developing one LTE plus NB-IoT base station, a unified base station, which is first of its kind. Like usually one base station means it will either do broadband or do IoT. So
Yeah.
now we are developing one unified base station which does both broadband and IoT. So some of that work we do, but the research part is separate from that. Some other implementation part that I do work with Lekha Wireless for that.
Yeah, that somehow we have to balance our theoretical work for publications and
Yeah,
this kind of implementation work where we can showcase and demonstrate the visible thing. So
yeah,
we have to do these things both.
yeah.
And there are a few questions in the chat box. So how machine
Okay.
learning will complement the signal processing techniques?
So see, that is the main thing. When we say signal processing, see, machine learning is also signal processing. So as we can tell that a machine learning algorithm is better and it can be used here only if you prove to me that it is better than the conventional algorithm. So that is what is missing in most of the literature. What they do is they will show their machine learning algorithm, compare it with other machine learning algorithms. Great,
Yeah.
fine. I'm very happy with it. But conventionally, we'll be doing some correlation based method or compressive sensing based method. Compare with that and tell, no, like whether using machine learning is really beneficial. So that is why you read any industry white paper, they will not say I'll be using machine learning for communication yet. Yet they are still coming up. So they won't say that I have adopted machine learning based. They will do for all other things like say your text prediction. Google openly tells we use machine learning for text prediction or your whatever your activity analysis, etc. But none of them can claim that they are using machine learning to communicate data. Nobody is claiming that yet because we still don't have a result showing that using machine learning is better than using conventional, especially when it
Yeah.
comes to communication receivers.
Yes.
Yeah.
And the next is like that hardware requirements in 5G compared to 4G.
Yeah, so hardware requirements in 5G, of course, are a little more difficult compared to 4G. So, see, strictly speaking, I can use the same 4G hardware and try to implement 5G. Only thing is, I might not be able to give you the features that 5G supports as such. So it will follow NR protocol, but finally it will give data rates like LTE. So then we cannot say that it is truly 5G then, right? Like someone was making this pure 5G statement yesterday. Then we cannot say it's actually 5G. So that's why it will require new hardware. So when we say requirement, I would say as faster. So typically a base station in terms of physical layer is an FPGA and a DSP. Okay, you will need a faster FPGA and a faster DSP, and more importantly, you need more storage. 5G is based on lot of context. It stores lot of your context so that it can give you better service next time. So that storing capability should increase.
Okay. And so yeah, one of the participant Afsar, he is telling provide an FDP training course underwater well. Yeah, Afsar, we are also in fact we have planned for that as well. Yeah, short course in underwater communication. So that will be maybe in the winter. I will announce that. Particularly, I have noted your email, so I will intimate you for sure. And there is another question: the difference between Type 1, Type 2 hybrid automatic repeat request protocol. Okay, I think
Okay,
yeah.
that is, yeah, that's straightforward. I think I told it, I didn't mention it as type 1,
Yes.
type 2 yesterday. So type 1 is chase combining. That is, you don't send parity bits. You always send the same information bits and directly combine the bits at the symbol level. So you directly combine the modulated bits. That is type 1. Type 2 will be you are combining it at a bit level after demodulation. So if you combine it before demodulation, it is type 1. If you combine it after demodulation, it's type 2.
Yeah. And what about the for the handover management in 5G NR? Can we apply the grant free access?
Handover management, again, it's an open item. I think,
Yes.
I don't know whether the person observed it in my diagram there. I have written mobility management also under grant free. It's still being discussed. It is not yet confirmed. So the thing is this, you can manage the handover, but you cannot do the handover. I hope I was clear. What I mean is, you can identify which base station you have to hand over to, but you can't hand it over to that base station because that requires your original procedure only as of now.
Yeah.
Identification can be done.
Yeah, Venkatesh Kumar, you can unmute and speak since you wanted to discuss directly.
Sir, when we are using machine learning, some of the data sets what we are getting is generally the data sets we want to uh, segregate what are the parameters we need. But most of the data sets what we have is suppose we need about SNR data is the most thing, but they have in mobile station there what are the internet access some dB level they will give,
Correct.
SMS dB level they will give, so many
Correct.
parameters they are giving.
Yes.
How to segregate that, and voice for voice particularly we are not getting the SNR.
Yeah. Okay. It's a very difficult problem. See, that is one more thing why machine learning in communications in the real world is slowed down because of this lack of data actually. So one thing is, as you told, when you get data, you know what is happening. To be very frank, people only are giving you logs. So basically, see, there is a Qualcomm mobile device, or Qualcomm's modem is there, or Samsung's modem is there, or someone else's modem is there. Typically, when people code in industry, no, there is something called enable logs. So when you enable logs, some printfs will come on a screen, which will be printing the different levels. That my power level is this, my received RSSI is this, and so on. Okay. So when you ask for data, typically you end up getting these logs, which are not filtered versions of the data. So, I mean, unfortunately, I don't like to say this, but yes, what happens is you will end up writing some parser first in Python. You will have to write your own parser. Parser looks for keywords. So, for example, you want to collect RSSI, received signal strength indicator. If you want to collect that data from that huge log you have to write a parser which identifies this keyword and takes the value beside it every time it identifies the keyword. Okay, so you have to build your own parser in Python to filter out the relevant data from this entire big log. There is no shortcut there, unfortunately. So you will not find someone who is doing it for you, because you ask anyone who has done it, he'll say, I have spent enough time doing it, so I'm not going to share this for free. Okay, so you will have to build your own parser for it. And secondly, for voice data, privacy issues are there. Nobody is, especially cellular communicated voice, nobody is ready to give you the voice which went over the line, right? Because you will be overhearing someone's conversation then. Even if you even if you anonymize the speaker, what they have conveyed you can always find out. So nobody is going to give you voice which has been transmitted over the cellular line. So you have to again build your own database for it using some standard voice samples or something like that, unfortunately, if you are talking about voice over cellular. But if you want any speech related data, that is there are a lot of speech related data available in literature.
Actually, I made my own data set with the SNR, and we applied it with the machine learning things.
With
Considering
SNR for what? For what?
uh, that is for spectrum sensing for
Okay,
cognitive
for
radio.
spectrum. Yeah, got it.
But
Hmm.
building our own, because when I refer the data sets,
Hmm.
these mobile phones data sets, how much time it is active, because we want to
Correct.
sense the unused
Yes.
spectrum only,
Yeah.
that we are unable to get from the data sets.
So
Is
that
it
you
right,
should,
sir, that approach
that
when we
approach
build
is
our own?
correct. Correct. That approach is correct. If you want to identify how much time the mobile is active, firstly you should know which protocol it is using. So in LTE or in 5G, for example, the active starts, you can assume that the active portion started from that RRC connection request. So there will be a message called RRC connected in that big log that you have. If it's a 4G phone, you will have a message called RRC connected or radio resource configuration established, something like that. Radio configuration established, connected, something on these lines. There will be a message. Then there will also be another message that RRC session ended, something like that. So established ended, connected ended. You have to find those pairs, and the time difference between that will give you the active time.
Thank you, sir. Thank you.
Yeah, okay. Thank you, Naveen. I think you have taken a lot of time, and in fact, you have agreed to take 2 sessions and the subsequent days, and it's our pleasure. We have covered very important topics in a very light way.
Thank you. I mean, I am always trying to give the big picture. Specifics I can give a more easy talk actually. Making this was more difficult. Like if you ask me to sit and derive that equation, I can do it very easily. But yeah, trying to convey the big picture always takes more time.
Yeah.
So thanks a lot. So I will communicate through email.
Yes, Naveen, sure. So yeah, I will get in touch with you again once I plan for other sessions too.
Yeah, sure.
Yeah.
Okay.
Thanks, Naveen. See you.
Thanks a lot. See you. Bye.
Okay, I think Lakshmi, I think you have joined. So shall we start?
Yeah, can you hear me?
Yeah, you can.
Am I audible?
You are audible. Yeah.
Yeah, okay, thanks. Let me just share the screen.
Yeah. Well, meanwhile, just let me introduce you to the participants. So I think we missed one lecture on as per our schedule. So I have rescheduled that. So instead of that, today our session will be starting now 4 to 6. So let me introduce a speaker now. And okay, now the speaker is going to talk about some graphical models, and you will get to know the details shortly. So he is an assistant professor in Department of Electrical Engineering, IIT Palakkad. He pursued his PhD in wireless communications from Indian Institute of Science and MS from IIC Bangalore. And he got his Bachelor of Engineering in Electronics and Communication from Anna University, Chennai. And he obtained his postdoc fellowship from Department of EECS, Syracuse University, New York. And he also served as a visiting assistant professor in Department of ECE, McMaster University, Canada. And he had a couple of industrial work experience as a software engineer and staff software engineer in National Instruments R&D and as well as Cisco Systems R&D section. So I convey my thanks and warm welcome to Dr. Lakshmi Narasimhan. So over to you, Lakshmi. Please take it over the session.
Thank you for the kind introduction. Can you see my screen? Is my screen visible?
Not yet. Just a minute. So it normally takes a couple of minutes.
Okay, because I'm getting a message which is saying the window is being shared.
Okay.
Okay. Should I stop sharing and try again?
Yeah, you can, but anyway, it will. But however, you have joined with the Teams app, right?
I don't have the app, so I'm just joining through the browser.
I see. Okay, let us see. Sometimes it creates problem. Let us.
Is it visible now?
It is showing that you are trying to share something, but the screen is not yet visible.
Let's see. Try again. Is it visible now?
No.
Okay. Is it a problem of joining through the mobile, sorry, not the browser?
Sorry, say that again.
Is it a problem of joining through the browser?
Yeah. If you join through the browser, it creates this problem.
Okay. Is it visible now?
Not yet.
Not yet?
Not yet.
Okay. Okay, I've tried everything that I can. I think now I have to install the app then. Okay, let me try installing the app because I thought I'll join
Yeah,
with the
meanwhile, you
browser.
can share the slides. I can share for you.
Okay, I wanted to write on the slides. So it will be.
But by the way, when you share the screen, have you minimized it or is it open?
No, it is open.
Okay.
Sorry for this trouble.
Yeah, not an issue. So just I will be sharing that until you install that. No problem.
Okay.
Yes, Lakshmi, you are in.
Can you hear me now?
Yeah, I can listen to you now. Yeah, now you have started sharing something. Yes, it is visible now.
Oh, okay, thanks. Sorry for
Yes.
this technical.
No problem, Lakshmi. Please take it. Okay.
All right, thank you. So let me start. So what I'll discuss today is a little bit about basics of probabilistic graphical models and how you can design signal processing algorithms for demodulation and decoding for receivers in 5G. So first I'll start with the basics of probabilistic graphical models. So before that, slight motivation. So why specifically probabilistic graphical models for 5G, and the reason why we need these models instead of regular maximum likelihood based receivers or demodulators. So the main reason is we have very large dimensions in 5G systems. We have these MIMO systems which are known as this massive MIMO, large scale MIMO. And the spectral efficiency and the sum rate in these systems are really large. The dimensions of the signals that we work with are really large. So the number of antennas we have are in the order of hundreds, and the base stations have even up to 256 antennas and so on. So the complexity of decoding such signals becomes really high. So typically, if you see in millimeter wave systems, which are now part of 5G, they have 128 antennas, even in a small patch of receivers. So typically in millimeter wave systems, we have base stations which have almost even 300 or 600 antennas. So the complexity of the signal processing algorithms becomes really huge, and sometimes it's exponentially high that we cannot use traditional statistical signal processing algorithms. So we need something which will have a low complexity and still perform really good. So we need near optimal performance, but at a complexity which is executable by current hardware. So this is where probabilistic graphical models help us. So I'm going to refer to this paper. Predominantly, most of the graphical model content in this talk will be from this paper by Sishang and others. So the paper is titled Factor Graphs and Some Product Algorithms. So a factor graph is basically nothing but one kind of a graphical model. And the sum product algorithm is basically a kind of inference that is run on this graph so that we finally identify some some estimation or deduction problem. So the entire goal in our talk is to solve an inference problem, which will be, in our case, a detection problem, a detection or classification problem. So we'll have some observation. So let's call our observation y. From this observation, so basically it's a vector of dimension m cross 1. So we have m observations. And from this m observations, we are trying to identify what were the n variables which caused this observation. So in a typical MIMO system, if we transmit, so let's say there is a transmitter with n symbols being transmitted. So let's say there's a transmitter which has n antennas, okay? 1 to n. Then it will transmit a signal x, which is n cross 1. But what we would receive is something, let's say, which has only m antennas. So we'll have at the receiver a vector which is of dimension m cross 1. So from this observation, we need to identify what are these n variables. So that this is just one example of an detection problem. So in general, this is what we are going to try to solve today. So we have observations y, and from those observations, we'll try to identify what are these n variables that caused this observation. So these x1 to xn are called as variables, and this y1 to ym are called as the observations. So typical estimation problem would require some sort of a maximum a posteriori or maximum likelihood based inference. So what we would do is we would compute the posterior probabilities. So what we have here, these are the posterior probabilities. The first one that we have here is the posterior probability. And the next one we have here is the likelihood. So typically by using Bayes theorem, we would say we would write the posterior as a product of the likelihood and the prior. So the prior could be anything. So typically we assume they are uniformly likely. If we don't know anything about the prior, then we might use the likelihood, which does not assume any kind of probabilities on the transmit signal itself. So once we have this posterior probability and likelihoods, what we need to do is to find out what was the most likely signal that was transmitted. We would try to maximize this function, posterior function or likelihood function. But then we would still get a vector. So we would get an n cross 1 vector. But we would need to individually identify what was the transmitted symbol. So this we have 1 to n, right? So we have 1 to n symbols. We need to identify these symbols individually. So for that, we need marginalization. So we marginalize over all possible signals. So this fy that we have the function here is a joint function. So in order to identify the individual symbols from it, we need to marginalize over the rest of the symbols that are present there. So whatever is the function, either the posterior function or the likelihood function, in order to obtain the individual symbols, what we have to do is finally marginalize. That is sum over all possible other vectors. So the notation that we have here is this tilde of xi. So the tilde of xi means it is summing over all x1 to xn except xi. So that's the meaning of this notation that we have here. Sorry, is my screen visible?
Yeah, yes, visible.
Okay.
I think now you have stopped sharing it.
Is it visible now?
No, now only you have started. It will take a minute. So far it was visible. Just we were able to listen to your question. Yeah, now it's done. Yeah, you are on the statistical inference page.
Okay, thanks. All right, so yeah, we need to marginalize. So the main problem that we have here is we have to marginalize a function which has n different variables. And we have to marginalize for, so if I want to know the first variable, then I have to sum this over 2 to n. If I want to know the second variable, then I have to sum this over 1, 3, up to n, so on. So this is a computationally very expensive task, especially if this n is 100 or 200. So what we are now trying to see is, can we use some sort of a graphical model method to simplify or to reduce the complexity in this marginalization? And the most important property that we'll use is to see if the function that we are trying to marginalize factorizes into functions of this form. So in this case, we have taken an example. So let's say there are 5 variables, and this posterior probability or likelihood or some function. Okay, so this is typically called as the objective function. If this objective function factorizes into other functions, that is, if you can write it as a product of some other set of functions. So in this case, we have written this as a product of fa to fe. So these are other functions, and these functions are functions of some subset of these 5 variables. So we have these 5 symbols that we have to identify, and we have broken down this big function into product of some other smaller functions. And because it can be broken down into product of the smaller functions, it will be easier to perform this marginalization. And why is this relevant to us? Because in most cases, we have these probabilities. So these probabilities usually would be broken down into some form like this. So depending upon the problem, it could be broken down into some form. If they are independent, we can just simply write like this. So if they are dependent, then we cannot simply write like this. So this is if y1 is independent of y2 to yn, then you can just factorize in this form. If not, we'll have to again apply Bayes theorem and then factorize this joint, this conditional probability. We can factorize this using the Bayes theorem. So this factorization actually helps us to perform this inference very easily in a computationally less expensive manner. Okay, now let's look into detail how this particular example helps us to perform factorization over this graph. So first thing is we have to represent this as a graph. So otherwise there is no point in calling this a graphical model. So how to represent this as a graph? So we have 5 different functions and we have 5 different variables. And these 5 different functions, they take some subset of these variables as their input and produce some output, which when multiplied together, we get the final objective function. So we'll represent this relationship as a graph. So the objective function is factorized into some set of functions, and how these functions are connected to the variables. That relationship is what we use to construct a factor graph. So in this case, this is a factor graph that represents the relationship between the variables and the individual functions. So this kind of factor graph is called a bipartite graph or a Tanner graph. So what is special about it? There are 2 sets of nodes. So one set of nodes are known as the factor nodes, and the other set of nodes, they are known as the variable nodes. So the factor nodes are essentially nothing but that correspond to the individual functions or individual factors in our objective function. So in this case, these functions, these individual functions are the factors in our objective functions. They correspond to the factor nodes. And the variables that we have here, they correspond to the variable node. So in this example, we have FA has only one input x1, FB has only one input x2, FC has 3 inputs x1, x2, and x3. That's exactly what is represented by these edges here. So FA has only one input, so we have one edge between FA and x1. FC has 3 inputs, which are x1, x2, and x3. So the edge here in this graph represents that the variable it is connecting to is an input to that particular factor. So this is how you construct a factor graph. Now, from this factor graph, we'll apply or we'll use what is known as the sum product algorithm to perform these marginalizations. Let's take an example. Let's take one particular variable. So let's take the variable x1. Now, if I want to find out the variable x1, so what do we need to do? We need to marginalize this function. So that means I'll have to sum over x2 up to x5, all possible values of x2 and x5 in this function. Okay, so that means here I'll put a summation x2. Let's clean this up. So I'll just put a summation here, x2 to x5. So the first term, or the this function fp, it runs a summation, or it is affected by the summation only with respect to the variable x2, whereas this is affected with respect to variable x2 and x3, and this is x3 and x4, and this is x3 and x5. So that means what we can do is we can rewrite this and do the summation over x5 for this function first, and x4 for this function first, and then together x3, and then with that together x2. So we are basically distributing the summation inside, and this is the expression that we get if we distribute the summation. So essentially this is as good as just summing over x2, x3, x4, and x5. We just distributed the summation inside and we have written. So in order to compute the marginal value for x1, what we need to do is we have to marginalize, or we'll have to sum over all possible other variables. So this is called the summary for x1. So with respect to x1, what is the summary? Is to marginalize or sum over all other possible values of the other variables. So in this case, what we have done is we have removed the effect of all other variables. Now from this marginalization, you'll see only the effect of x1 in the objective function. So if we perform this, then we can identify what is x1 and we can detect what is x1. So how is this graphical model helping us to compute this? So what we see here is next, the sum product algorithm. The sum product algorithm tells us that you send some messages from the variable node to factor node and factor node to variable node. So that is, so we have this factor nodes here and we have the variable nodes here. So the sum product algorithm tells that some messages are computed in this factor node, and then you pass it on to the variable node. And this variable node using that message will compute something and then pass it on to its factor nodes and so on. So once this messages are computed and passed on, and then when all the messages are computed and passed on, eventually at the end of it, we'll identify this total marginalization. So this sum product algorithm tells us how to compute the message between the variable node and the factor node and the factor to variable node. So we have just two rules. One, it simply says that the variable node to factor node message is just a product of all the incoming messages. That is, at every variable node. So let's take, for example, this variable node. So this variable node contains connections to 3 different factors. So that is, it will get message from 3 different factors. So this variable node, when it sends messages to these factor nodes in a later iteration, what this rule tells us is that just simply multiply all the messages that this variable node got and send it to the other node. That's all. So the variable node, that is the xth variable node, when it sends message to the fth factor node, what it does is it simply multiplies all the information that it got from other factor nodes which are other than this f itself. So if we have factor nodes 1 to, let's say, 1, 2, 3, and 4, and when this particular variable node is sending a message to the second factor node, it will multiply all the messages it got from 1, 3, and 4, and then send that as the message to the second factor node. So that is all, as simple as that. It simply computes a product. Now, what is the rule for computing the message at the factor to variable node? What it does is, now it also does the same thing. It computes the product of all the incoming messages. So a factor node f is sending a message to variable node x. So let's say these factor nodes are 1, 2, 3. Sorry, the variable nodes are 1, 2, 3, and 4. Now, if this factor node has to send a message to, let's say, variable node 1, it will multiply all the messages it got from variable nodes 2, 3, and 4. But now there is one more additional step. That step is employing the function that it has. So each factor node, remember, represents one particular factor or a function. Now that has to play a role here, right? So this is where that information is used. So we multiply all the message and then use the knowledge of what the factor is or what the function is, and then sum over all possible values of x. So this is where we are summing over all possible values of x. So we do a product and we do a sum, and hence this is called the sum product algorithm. Now let's see how to use this information to actually do the factorization. Now let's say if I want to perform this factorization, that is I want to marginalize x1 and obtain this factorization. Then one way of at least to explain what is going on is to see this graph as a tree structure. Now I can just redraw this entire graph as a tree with x1 as a root. So this is the same graph. The graph that is here is exactly the same as the one that is here. Only thing is now the structure is just redrawn such that it looks like it is a tree, but it is exactly the same graph. So what we have done now here is to show x1 as a root and then drawn the other nodes beneath it. Okay, and the same, if I want to marginalize x3, then what would I do is do the same thing, draw a tree which has x3 as the root node, and then draw the rest of the connections from this original bipartite graph and draw it as a tree. So you can pick any node here and then assign it as a root node and then draw a tree. So then you will get a different tree. So each time you will get a different tree, but all of these trees are exactly the same as this graph. Now let's draw a tree. Now the sum product algorithm tells us that start applying these rules that we have. So we have these two rules, how to compute the messages, right? So start applying these two rules to the leaf of the graph. So what are the leaves? The leaves are those which do not have any connections to any nodes beneath them. So we have x4, x5, fa, and ft. So these are the leaf graphs. So first compute the messages at these graphs. So what is the incoming message to x4, x5, fa, and fb? Nothing. So we can simply say the message is just 1. Now from that, we can compute the message that is going to fe, fd, and x2 and x1. So what will be the message at fd and fp? So this is at the factor. So this is a variable to factor node. Because it is a variable to factor node, so it is just a product of whatever is computed at x4 and x5. Okay. And now let's try and find out what is the message at x3. Okay. What is the message that is sent from x3 to fc? So x3 to fc is the factor, it is the, okay, so before that, maybe we'll find out what is factor to variable node. So let's say what is the message that is computed at fd? So we'll use this rule. So fd is connected to x4. So that's the message that it gets, and it has to send it to x3. So this will be mu of fd to x3 of x3. So this will be equal to summation over all x3 fd of x3, and the product, it is connected to only one, which is x4. Okay. So it is the message that is from x4 to fd. So this is the message that it gets. And this is forwarded to x3. Okay. And x3 gets the same message from fe as well. And this keeps on going. So here we have a summary of all the messages that we have. So let's see what are these different messages. So we have, I've written out everything, what happens from each node to another node. So in this case, so FA, clean up this. Okay, FA is connected to X1. So if you see FA is one of the leaf nodes. So fa to x1, that is a factor to the variable node, is just the function's value itself. Similarly, just the function's value itself. Because the variable does not contain any information, what it simply sends is just 1. So these are the first computed information because these are the leaf nodes. So these 4 are the leaf nodes. So the factor gives simply the value of x1 itself, and the variable does not contain any information, so it just sends 1. Now, from these leaf nodes, what are the other nodes that we have? So x1 is the next node that is connected to leaf node, x2 is the next node, and fd and fe. So those are the next that we could compute. Similarly, here, what are those? So that's exactly what we have written before, right? So we had computed this. fd to x3 is what we had computed earlier, right? So fd of x3 comma x4. So this is fd of x3 comma x4, and just the message from x4. And this is summed over all x3. That's what we have written here. Okay, so this is the next stage. All right. Now, once this is computed, we have to go one level above. That is, we have to compute the messages at the nodes which are connected to the variable nodes or the factor nodes that were connected here. So FC, let's see what does FC was connected to. So FC was connected to x1, and we have x3, and x3 was connected to fc. So we have to compute these messages now. So fc through to x3 and x3 to fc. We apply the same rule. So once again, we find out. So at the variable nodes, we always just simply multiply everything. We compute the product. And at the factor nodes, we take the product of all the incoming messages and also the product of the factor. Now, these FC and X3, what are they connected to? So that we have to again identify. So this X3 is connected to FD here, and X3 is connected to FE, and FC is connected in turn to X1 and X2. Now, once again, doing this step, we have to compute this all once again till we reach to the leaf nodes. So we start with the leaf nodes, and then everything goes up to the entire graph and then comes back again to the leaf nodes. So that completes the one full message passing. So once the messages reach the leaf nodes, remember that we didn't have any message initially at the leaf nodes because at the variable nodes, we didn't have any information, so we had one. Now the variable nodes would have obtained these information. That means the passing of the messages is complete. Now, finally, once the passing of the message is complete, at each and every variable node, we'll have some message, and that is summarized here. So the variable node 1 will have these as the messages. The variable node 2 will have these as the messages. Variable node 3 will have these as the messages, and so on. The interesting thing is, now these messages exactly correspond to the marginalization of whatever objective function that we had in mind. So let's take an example. So we have already marginalized out fx1, right? So let's see if this set of messages actually gives us the marginalization that we want. So let's substitute and see what happens. So if we substitute fa to x1, so we have to first find out what is this message fa to x1. So the message fa to x1 is simply fa of x1. Okay. And then we have to see what is fc to x1. So fc to x1 is what we have here. Now we have to go back and substitute what is x2 to fc. Okay. X2 to fc is this message, which is basically nothing but fb to b of x2. And what is x3 to fc? X3 to fc is the product of these two messages. And what is these two messages? So these two messages are once in turn these messages. So which is nothing but product of fd x3 x4 and the product of fe x3 x5. Okay. And these two messages which are just ones. Okay. So these are summations over all variables other than x3 here. That will be x4 in this case. So this is x5 and this case x4. Okay. And this is summation with respect to x2. Because remember, it is all variables other than x1. So substitute this here. okay, along with this FC x1, x2, x3 here. Then what we get is FA of x1 times summation FB of x2 summation FB of, so in this case it is all other than x3. So x3, which is FC of x1, x2, x3, and summation x5 is x3, x5, and summation x4 FD of x3 and x4. Sorry, my handwriting, I'm just trying to fit in this area. So which is exactly the same as what we had initially seen before here. So if we write out for each and every, if we just expand each and every message here, then it will be interesting to see that all these messages would have exactly given you the marginal values for each and every individual variables that we have. So all we have done here is we have just followed these two simple rules, computed the products, and then took the sum of the individual products along with the factors from each and every node. And then pass it along this graph such that we start from the leaf node and then once again end at the leaf node. So that completes one full message passing round. And at the end, what we see is the message at each and every variable node is exactly equal to the marginal value of the factor or the objective function that we have. So once we have this marginal, then all we need to do is just see what is the maximum value of this marginal, and that gives us the inference, or that gives us the detection problem that we wanted to solve. So one important thing to note here is this factor graph does not always have a cycle. So this entire algorithm works well as long as this factor graph does not have a cycle. What happens if there is a cycle? So what do I mean by a cycle? So let's say there was another connection, something of this form, like this. So that means the messages that are from FA to X1 will go in this direction, and then go to FC, and then go to X3. From there, X3 again, it will go to FA. So there is a cycle here in this graph. If there is a cycle in the graph, then you cannot write it down like a tree. So any graph could be redrawn as a tree only if there does not exist a cycle. So if there exists a cycle, then what happens is, then the messages start running in a loop. Then you don't know when to stop. So the biggest problem that happens when there is a cycle is you need to know a stopping criteria. So at least now, till before not having cycle, we knew that we start from the leaf nodes and then come back to the leaf nodes and stop. But then once there is a cycle, there is no leaf node, right? Because every node is connected. So in this case, if FA is connected to X3, it will be like this. Then you'll not be able to know what is the leaf node. So it will just keep looping here. So that means we need to know when to stop passing the messages. So when there is a cycle, then we need to say that, okay, we have to fix some criteria, and that will depend from problem to problem. So we'll see some examples. So a particular stopping criteria could be used to say, okay, this is when we'll stop passing messages. So this is the general idea of computing messages and message passing using what is known as the sum product algorithm in probabilistic graphical models. We'll see some examples, especially that are relevant to 5G, where these graphical models and this message passing algorithm could be used for detection and decoding and demodulation and so on. The first and the very famous example is the LDPC decoding. So LDPC is nothing but an error correcting code known as the low density parity check code. So it simply says that consider an error correcting code which takes k bits and produces n bits as the output. So typically k is much smaller than n. So for example, it takes 100 bits and then produces 200 bits as the output. So that means it adds redundancy. So that is what is used for correcting errors. Now we could actually represent this coding process using a factor graph. And that factor graph is constructed using what is known as the parity check matrix. So parity check matrix is a property of an LDPC code. If you have an LDPC encoder, each encoder has an associated parity check matrix that says how the codes are constructed. So for example, if this is the parity check matrix, so in this case, there are, so the dimension of this matrix is 3 cross 6. So typically if we use an k by n code, then the dimension of the parity check matrix is usually of this form, that is n minus k cross n. So here n is equal to 6 and n minus k is equal to 6, which means k is also equal to 3. So we have a rate half code, that is k by n is half. Okay. Now this is one example of a parity check matrix. As you can see, there are a lot of zeros in it, and hence this is called as the low density parity check code. And the property of the LDPC code is that if someone gives you a parity check matrix and an LDPC code word, which is encoded using that particular parity check matrix, let's call this B, which is nothing but a 6 cross 1 vector, which is encoded using. So let's say someone gives you a 3-bit input, and that is given to an LDPC encoder, then you get a 6-bit output. Now, if this LDPC encoder has used the parity check matrix F, then this output, let's call this as vector B, will satisfy the property that FB is 0. This F times B is 0, which means this output vector lies in the null space of this parity check matrix. So that is the property of the LDPC encoder. Now, if this is an LDPC encoder, then if there is a valid code word that we multiply here, then what we will see is, we'll see that this will be equal to 0. So that is, let's say this has 6 variables. Then remember, these are all, these additions are performed in finite field, which means you cannot simply add 1 plus 1 and say it is 2. So it is in the binary finite field, which means what we have to do is we have to XOR the bits that we have here. That is, we would say B1 XOR B2 XOR B5 is equal to 0. That's what the first row tells us. And the second row tells us that B2 XOR B3 XOR B6 is 0. And the third row tells us that B1 XOR B3 XOR B4 is 0. So we have these 3 constraints. So any code, any code word that we obtained after this LDPC encoding should satisfy these 3 constraints. And this check matrix is exactly what that we are going to use to construct a graph. So in this example, if we want to construct a graph, we'll, as usual, draw a bipartite graph. Okay? So that bipartite graph should contain 2 sets of nodes. So one is the variable node. That's easy. So we have 6 variables here: B1, B2, B3, B4, and B6. And what we have here are 3 factors. So these are the 3 functions, right? So we have 3 functions here. So let's say there are 3 factors. So in LDPC coding theory, this is also called as the check nodes. They're also known as the factor nodes. So let's call this as factor 1, 2, and factor. So the first factor, let's say this one, is connected to variable 1, 2, and 5. Second one is connected to 2, 3, and 6. And third one is connected to 1, 3, and 4. Now we have a bipartite graph here, and we know the functions here. This FA, FB, FC. Let's call this FA, FB, and FC. And we have some variables here. So all we need to know is find out what is f of BI. So if we marginalize this, let's say we want to find out the likelihood. Let these f's be likelihood. So if I want to find out the likelihood of the bit I being 1 or 0, that's the decoding problem that we have. Is this 1? So what is the likelihood of this being 1? If this is greater than the likelihood of this being 0, then we simply declare that BI was actually 1. So we don't have to compute these 2 separately because they add up to 1. So if I just compute this likelihood, and if it is greater than 0.5, then we say that this is highly likely to be 1. That's all. So in this case, we don't have to compute multiple, or we don't have to evaluate these functions for all possible values of bi. All we need to do is just evaluate for bi equal to 1. That is sufficient, because bi equal to 0 is just 1 minus this value. Okay. So we can just use the algorithm that we had just seen before. And I'll just summarize briefly what the steps are. So we just initialize the variable nodes with. So remember, in the algorithm initially we said the leaf nodes have just one, right? The variable nodes just had one. So in this case, we initialize them with the prior probabilities. So these prior probabilities are nothing but what is the probability with which the bit will be 1. In this case, A is just 1. Okay. So if they are all equally likely, then we simply say it is half. That's all. The prior probability of that being half. Then once the variable node messages are known or the variable nodes are initialized, we find out the check nodes. The check nodes are nothing but the factor nodes. And we just compute the probability. So what is this f? This f, remember, this f represents that this function is equal to 0. And also we said finally the f that we want to compute, the objective function that we want to compute is the likelihood. So what we are trying to find out here is the probability or the likelihood of this value being equal to 0. That is likelihood of b1 XOR b2 XOR b5. What is the likelihood of that being equal to 0? That is, what is the likelihood of that particular condition, the check condition, being satisfied? That is what we know, the event of the check equation being satisfied, meaning that this row or this function fa, this factor function fa, what is the likelihood that it gets satisfied? That is the probability. That is the value of the function fa. If I want to evaluate fa, then fa in this case is nothing but the likelihood of this check equation being satisfied. So that is the message that we compute here. So remember, the message that we had here is multiply with the prior probability. That is a message from the variable nodes and the likelihood that you compute here. So the interesting thing is you're multiplying prior probability with the likelihood that you're computing here, which means essentially this algorithm performs a posterior probability calculation. So remember, the definition of a posterior probability is likelihood times the prior. So we initialize the variable nodes with prior probability. And then at every check node or every factor node, we compute the likelihood. And then the message is, in fact, the product of this likelihood and the prior. So it so turns out that at every point, we're computing the a posterior probability. And then we iterate between updating the prior and the a posterior probability. So if you see what happens at the variable node, it takes into account all these a posterior probabilities. So variable nodes just simply multiply. So that's the definition of sum product alpha. It just simply multiplies all the input it has. So it updates the prior. That is what happens here is we said, I don't know anything about what are the actual bits. So I assume that they're all, it could be either 1 or 0. So I say that with probability half, it could be 1 or 0. Now, once I get the initial a posterior probabilities or the posterior probabilities, then I'll update my prior here. So these messages, in fact, are nothing but the priors at the variable node. I'll update my probability of this variable, that is the bith variable, being equal to 1. That by simply multiplying all the incoming posteriors. So once I update, now I have a new prior. Now I'll send out that prior to all other connected factor nodes. And once again, with the updated prior, the factor nodes compute the new posterior probability. So essentially what happens between these two layers is computation of computation of posterior probabilities and updating of prior. That's all is happening. So this is in this particular example, the sum product algorithm gives a different view of what is happening inside these nodes. So the actual description of sum product algorithm is quite abstract. It does not tell us what is this FA, or does not tell us what is this FB. It can mean different things in different problems. In this particular problem of LDPC decoding, because we have set F function to be as likelihoods and the initial probabilities as the priors, it so turns out the messages, each and every messages, the variable node to check node message turns out to be the prior probabilities, and the variable, the check node to variable node messages turns out to be the posterior probabilities. But remember, we cannot guarantee that this graph does not contain a cycle. So in this very example, it contains a cycle. So here, I think, so we have a large cycle here. Yeah. Connection, disconnection. Yeah. So we have a big cycle. So this shows that there is a cycle, which means that this message passing will keep on looping forever until we stop. Therefore, we need a stopping condition. So the stopping condition that we know that if, let's say at every point you update the prior probabilities, and then at some point of time, you say that the probability of B is equal to, let's say 1 is almost 0.99. Then you declare that that particular BI is 1. Okay. Now we construct, let's call this BI hat. Okay. So B1 hat up to B6 hat. And then we multiply with this F. Okay. And then we see, is this equal to 0? If this is equal to 0, then it is actually a valid code word. Then we could have corrected all the errors. This decoding process would have corrected any errors. If it was not a valid code word, if the received signal was not a valid code word, then this would not be equal to 0, which means some of the bits are in errors. So what do we do is we keep running this step 1 and step 2 until we see that this FB is equal to 0. So that is a stopping criteria here. Whenever there is a cycle, we need to put a stopping criteria, and that stopping criteria is problem dependent. And in this problem, the stopping criteria is that keep running, keep updating the priors and posteriors until you see that it is a valid code word. It satisfies the property of a valid code word. Okay, so this is the very famous LDPC decoder, message passing decoder, or the sum product algorithm. So how is this useful for a massive MIMO system? So massive MIMO is the most common physical layer setup for 5G systems. I'll briefly describe what is a system model for massive MIMO systems. So I'll consider a multi-user MIMO where there are K users, and each of these users have NT antennas. So if we have a mobile cellular network, let's say there are K users in a cell, and they connect to a base station. The base station has N antennas, and each of these mobile users, let's say they have NT antennas. It could be 2 or 4, or if it is a laptop, it can be 8, and so on. Now, there is some factor known as the alpha, which is the loading factor. If the base station has N antennas, then how many users can it support? So that is known as the loading factor. Sometimes this is also expressed as KNT by N. So there are different definitions. These are the two most commonly used definitions. So when alpha is equal to 1, then it means that the system is fully determined. That is, there are K and T variables, and there are N observations. So if you write it as a linear system like this, then you have the number of unknowns is equal to the number of observations that we have. So if alpha is 1, it is fully determined, and if it is alpha is less than 1, then it is underdetermined. And sorry, if alpha is greater than 1, it is underdetermined. Then we'll have more number of unknowns. And if alpha is greater than less than 1, then we have overdetermined system. So that is, we have more observations than the number of unknowns. So alpha that tells us if the system is underdetermined or overdetermined. So these are the variables that we have. Xc is the transmitted signal. That is, it contains all the signals from all the K users. This is typically the uplink. So that is, so we are considering the uplink. We have K users. Each one have NT antennas, and then they transmit and the final signal. So each one has one portion, X1, X2, and so on. Okay, and all put together, we'll say one vector X, and that is X1 to Xk. So this is the vector that we need to decode at the base station. The base station gets vector Y, and that is through this MIMO channel H. So we say Y is Hx plus this Y. So this is all typically in the complex domain. The C represents that these are all complex numbers. So the probabilistic graphical model algorithm that we saw so far, it can be used even for complex numbers. But for simplicity, we reduce it to real so that the explaining becomes easier. But it's applicable directly even in the complex domain. Okay, so we reduce this model that we have to real numbers. And to do this, we do a simple reconstruction. We have to just increase the dimension by 2 everywhere. So the y vector, which was just n cross 1, now becomes 2n cross 1. This yc, which was n cross 1. Now this real, which was complex n cross 1, it becomes real 2n cross 1 and so on. Similarly, the matrix, which was n cross k, now just becomes 2n cross 2k. That's it, and so on. Now, finally, we have this system, a real system where all the values are real, and we have y equal to hx plus n, where h is some wireless fading channel, and x is a set of symbols that were transmitted by the multiple users in the cellular system. And what we say is this x now belongs to a set of pulse amplitude modulated constellation. That is, they contain this xi is some plus or minus 1 or plus or minus 3 or something. The maximum size of the constellation is m. So it is up to plus or minus. Why we say this is, then it becomes that xc belongs to some QAM, that is, it belongs to mQAM. If it belongs to mQAM, then along the real axis we have root m values, and along the imaginary axis we have another root m value. So if we have plus or minus I, plus or minus j, then it corresponds to this one real number here, other real number in the imaginary axis. So the QAM, these constellation points, when observed along one particular axis, either the real axis or the imaginary axis, we get the PAM signals. Okay. Now let's say we have the knowledge of this H matrix at the receiver, at the base station, where that's the receiver that we have here. At the base station, we know, let's say, somehow through channel estimation, the H matrix. And now we have received Y. From that, we have to identify what is this X. So because of this H matrix, each Yi that we have, let's say Yi that we have, is going to be summation over J, Hij, Xj plus some Yi. That is, you can see here, we have interference from all k variables, that is all kx variables. So we have to cancel out this interference. So if we use successive interference cancellation or parallel interference cancellation, the complexity is going to be really huge. Or if I want to simply compute the maximum likelihood probability here, then I have to compute the maximum likelihood for all possible values. So what are the all possible values that we have here? So if I simply take x to be, let's say 2k cross 1, and x as just plus 1 minus 1 and nothing more, then the different possible values of x is 2 raised to the power 2k, which is huge. If k is just 10, this becomes 2 power 20. So the computational complexity of computing maximum likelihood becomes 2 power 20, which is huge. So we need some low complexity algorithm. And we'll use this factor graph based method, and we'll employ some product algorithm. And we'll see how to use some product algorithm here. So first thing is to construct the factor graph and identify what are the product functions. So once again, what we need to do is we have to compute the likelihoods, right? So that's all we want. So if we are going to try and do map detection, that is a maximum A posterior detection, we have to write the map equation. And this is the map equation. The map equation factorizes into the likelihoods and the prior probabilities. So in this case, let us say, to make things simple, let us assume all the constellation points that we have are equally likely. That is, it could have been any constellation point could have been transmitted with equal probability. So if we have m points, then the probability of xi being one of the particular constellation values is 1 by m, uniformly distributed. Okay. So we have to construct this graph. And how do we construct the graph? So this is how we have to have the variable nodes. These are the variable nodes. And these are the factor nodes. So what are the variable nodes? Variable nodes are essentially the variables that we need to identify. So in this case, we have x1, 2, x2k. These are the 2k variables that we are trying to demodulate at the receiver, at the base station. So those are the variables whose values we are trying to find out. And what are the functions or what are the factors? The factors are nothing but the observations that we have. So if you observe here, So this likelihood is what we have, and this likelihood you can split it into y1 up to yn, right? So this is exactly how many factors that you can split into, which means those are the factor nodes. So in this case, the factor nodes are also the observation. So we say that either we call them as the observation node or we call them as the factor node. Now, what are these messages? So if we could compute these messages, then we are done. Then we can find out the solution to our problem. We can find out how to perform marginalization of the symbol probabilities. Once we perform marginalization, then we have demodulated. Okay? So there are some interesting tricks that we can use, especially in massive MIMO systems. So those tricks are coming from central limit theorem. First thing is we are going to use the Gaussian approximation. So let's see how to use Gaussian approximation. So these tricks will actually help us reduce the complexity of the messages. So first we observe that, so we'll rewrite this equation that we had written earlier. We'll rewrite this equation. Okay? We'll rewrite this equation here as yi is equal to hij xj plus zij. So remember, we had just a summation here. So we'll rewrite this entire thing as this. So every observation, every ith observation, we'll express this as a function of the jth variable node plus some interference term. And that interference term is given by this quantity. Okay? This is the interference from all other variables plus the noise. Now, because this is a massive MIMO system where the number of transmit signals are huge, let's say there are 100 users in a base station, then by applying central limit theorem, all the users are all going to be transmitting independent signals. So because of these variables, all these variables being independent variables, we'll use central limit theorem and then we'll approximate this entire summation to be a Gaussian distributed random variable. So this helps us in reducing the complexity of computing the message. Otherwise, computing the message, which is the likelihood for each of these variable node, is going to be really high. So what we do is we just use this property of central limit theorem, which comes due to the dimension of the massive MIMO systems, and then approximate this to be a Gaussian distributed random variable. So once it's a Gaussian distributed random variable, there are only two parameters that we need to compute to summarize it. That is the mean and the variance, nothing more. So to compute the mean of it, all we need to do is just find out this quantity. So remember, we said that we'll know what is the channel gain. So all we need to do is find out the mean of the other variables and the variance of the other variables. So once we know this, we can find out the likelihood. So remember, the individual factors we said are nothing but yi. Those are the individual factors that we need to compute. And these would be the messages from each of the factor nodes. So each factor node will get the posterior probability from their variable nodes. So remember what the variable nodes do. The variable nodes simply multiply all the messages that they get. Whereas the factor nodes, they multiply all the messages and apply the function that they have, or the factor function that they have. So the same thing happens here. The variable nodes just multiply all the probabilities that they get, whereas the factor nodes, they apply the factor value that they have, or the functions value that they have. And like I said, each problem will have their own interpretation. In the case of LDPC, we had the prior and posterior as the interpretation. And in the case of MIMO demodulation, the messages, the variable node messages are nothing but the posterior probabilities, and the factor node messages are nothing but the likelihoods. So what we do here is we update the likelihood using the posteriors, and we update the posterior using the likelihood. And this has this posterior and likelihood because in this case, we assume the prior is uniform earlier, and then we are substituting the posterior instead of the prior. So we keep passing this, but remember, this is a fully connected graph. Every node is connected to every other node, which means that it is full of cycles. So that means we need a stopping criteria. The stopping criteria is typically say that till the probabilities converge. That is, if I have the algorithm written down here. We say that stop if the previous probability or the previous message that you have computed is same as the current message. So if every message seems to be the same, then passing it over and over again will give us the same message. So this is the stopping criteria that we are going to have. So I've just summarized the message that we have. So the message at each variable node is given by product of all the incoming messages, and the message at each factor node or the observation node is just applying the factor that we have. One interesting thing to note here is till now, till the LDPC decoding, whatever we saw, each factor had just one value. That is, it is compute the value at some variable value of 1 or 0. And we said the other one is anyway equal to 1 minus that. And so we are okay with the messages. So messages were nothing but scalar quantities till now. But in the case of MIMO decoding, scalar quantity messages don't really work. That's simply because each of the variable can take multiple values here. So if we see here, yeah, each of the variables can take more than 2 values here. So which means having scalar messages does not really help. We need to do the marginalization for each and every value of the variable. So each variable can take multiple values. So that means the messages themselves should be vectors. So what I'm trying to say is, let's say if the variable x1 was just taking either +1 or -1, then the message can just be m of x1, which is equal to, let's say, +1. Then I need not compute another message for m of mu of x1 equal to -1, because this is sufficient as long as it represents probability. The mu of x1 equal to -1 is just 1 minus this quantity. Okay. But if x1 can take, let's say, +1, +3, or -1, -3, then we need to compute this vector mu. This mu1 now becomes a vector. Okay. And that contains for value for x is equal to +1, value for x is equal to +3, value for x1 is equal to -1, and so on. So each message now becomes a vector. Okay? And hence this is also known as the vector message passing algorithm. So the traditional sum product algorithm was designed for a scalar setup, whereas now we are extending this to vector setup so that we can use this for decoding and demodulation in massive MIMO systems. And yeah, so remember to compute this message at the observation node or at the factor node. What we are using is we are using all the messages from the other variable nodes, and these are the probabilities, which means this will these are the probabilities, and these are the individual. The vector s here is simply nothing but +1, +3, all the values that the symbol can take. So S transpose Pi Li is nothing but the expected value of, in this case, Xi. That's all. So we take the probabilities from all the variable nodes and then use them as the posterior probabilities on each of these symbol values. From them, update the new factor node message. So to summarize, this is the algorithm. So initialize the probabilities, the variable node prob. Always remember the variable nodes should be initialized to something. So the sum product algorithm said initialize to 1. And this initialization varies from problem to problem. In all our problems, we'll initialize it to the uniform distribution. In this case, this is the uniform distribution. And then compute the factor node message and the variable node message. Okay, and the factor node message is nothing but the likelihood. So this is the likelihood, and that is the factor node message, and the variable node message is just multiply all the likelihoods. That's the variable node message is always the easiest. Just simply take the product. Whereas the factor nodes is where we'll have to apply the knowledge of the factor functions that we have. And this is another interesting step which is applied for cyclic graphs. The convergence in cyclic graphs is found to be slower because of the existence of cycles. And to speed up this convergence, what is recommended is to use what is known as damping, which is nothing but if you've computed a message at mth iteration, then just don't use that message directly, but then take a linear combination of that with the previous message that you had. So if I have some message, let's say V at some iteration M, then I could take a convex combination between the previous message. This is found to be speeding up the convergence. In optimization, this is also known as this Nestrov's acceleration. This is similar to Nestrov's acceleration, where what we do is we take a convex combination of the existing message with the previous message. So this helps us to speed up the convergence, because whatever was the previous message, that information is also carried on. So you have some extra information along with every message. So this avoids us to get stuck in local minimas or maximas. So that's the idea behind using this damping. Finally, when do we stop? So we stop when the messages look very similar. The current message that we've computed, if it looks very, very similar to the previous message, they are almost equal, then we say, okay, then whatever messages that we pass anymore will also remain the same. So there is no point, stop there. So this is the stopping criteria. Or sometimes what is done is maximum number of iterations. Let's say 200 iterations. I don't want to run more than 200 iterations. Then that is also set as a stopping criteria. So we stop at some point. Once we stop at some point, what we need to do is we already have the posterior probabilities. We simply just compute what is the maximum symbol value that is there in the posterior distribution that we have. Essentially, the vector that we have is nothing but this vector that we have computed is nothing but a PMF. It's a mass function, which gives us the probability of xi being equal to +1 or +3 or -1, and so on. So we see which is the largest probability here, and then declare that to be the actual value of xi, which was transmitted. So this gives us the maximum a posterior probability decoding, that is map decoding. So if I want to run the map decoding, in this case, map decoding is same as the ML decoding because the prior probabilities are all uniformly distributed. So we have performed demodulation successfully by using this belief propagation or message passing algorithm. Okay, just skip that. I'll show you the results. So this is an interesting result. So what we have done here is we compare the massive MIMO demodulation performance with that of match filtering and MMSE, the minimum mean square error demodulator. This is the non-binary BP and this is the binary BP, which means non-binary BP is where each of the messages are nothing but vectors, and binary BP is where each of the messages are scalars. So we can expand the system and represent each and every message as a scalar. So that increases the dimension of the system even more. So we compare this performance of demodulating this entire massive MIMO system. The traditional MMSE. The MMSE is what traditionally that is used everywhere. And you see the performance gap between MMSE and the probabilistic graphical model method is huge. It is almost 10 dB difference. So the performance advantage is huge. And what about the complexity advantage? It also seems complexity advantage is also huge. So what we have done here is plot the number of computations required for the probabilistic graphical model method and the MMSE, this is zero forcing and this is the match filtering for a particular SNR. So in this case, we have fixed an SNR of 17 dB and we have 128 antennas and 16 QAM being used for the modulation. So the gap is also huge here. So if you see here, almost 1 million operations are used for the belief propagation method. At the same time, almost 20 million operations are used by MMSE to perform the demodulation, but the performance is extremely poor. So despite using more computational power, the performance of MMSE, which is a traditionally used demodulation algorithm, is really bad. And this is because massive MIMO systems have massive amount of interference. There are so many antennas, so many transmit signals, and this so much of interference is it's causing havoc in MMSE receivers. The MMSE is not able to cancel out so much interference from so many antennas. Whereas the probabilistic graphical methods, they perform marginalization, and then they give us the same performance as good as that we have at small number of transmit antennas. This is the advantage of using probabilistic graphical models for massive MIMO systems, where the complexity is almost an order lesser and the performance is almost 10 dB better. And the dotted line that we have here, this is the lower bound. We cannot get any better than this performance. This is the AWGN performance, which means that's the lower bound. So AWGN means there is no interference. So we are decoding without any interference. It's equivalent to decoding without any interference. And as you can see at high SNR, the graphical models give us a performance which is equivalent to removing all interference. So the interesting point to note here is as the dimensions increase. So this also, you have to see that this pink is 32 and this is red is 64 and 128 and so on. So as the dimensions increase, that is the dimensions of the graph that we have increases and the SNR increases. As the SNR increases, the performance of the message passing based demodulation is very close to the ideal demodulation that is possible. This is the theoretically best demodulation that we can do. You cannot get a performance any better than this. So which means we are going as close as to the theoretical best when the dimensions of the problems are higher. And this also says that the belief propagation methods are appropriate when the dimensions are large. For smaller dimensions, if I use this for n is equal to, let's say, 4, there are only 4 antennas, then this will be very close to MMSE. This will be as bad as MMSE itself. So as the dimension increases, the convergence of these belief propagation algorithms improves and they perform really well. That is one key takeaway that we can see here. Now, another interesting aspect of large dimensions is what is known as this channel hardening. So we'll see what is channel hardening and we'll see how to exploit this channel hardening in probabilistic graphical model based receivers. So the channel matrix H, we assumed in the previous conditions, in the previous receiver or demodulator to be a known matrix. What if it is not known? Then what do we do? So in this case, once again, we exploit the property of large dimension. So large dimensional random matrix theory has one interesting phenomena known as the channel hardening phenomena, which is given by this Marchenko-Foster law. It says that if this H matrix that we have, the channel matrix, which we saw to be some n cross k and t, right? So if these n and k are really large, then this H Hermitian H normalized by the dimension n almost becomes an identity matrix. This is quite interesting because it says H is a random matrix. It can be anything, but whatever it is, whatever instance it is, you just randomly take an H matrix, a channel matrix, compute H Hermitian H, and normalize with the dimension, then that will look very close to an identity matrix. And if we simulate and see, this is what we see. For n is equal to 32, this is what we see. So these plots are nothing but H Hermitian H or H transpose H, where we take the H matrix, convert it into real, and then plot the real equivalent of the H matrix. For n is equal to 8, obviously it does not look very nice because the dimensions are very small. Remember, this law is applicable when n and k become very large. So for 8 and 16, it doesn't really look great. But the moment we go to 64 antennas, then this is really close to an identity matrix. So that means we need not spend much time in doing channel estimation at all. All we need to know is to know the statistics of these off-diagonal terms and this diagonal terms. So we have an identity matrix, and this is technically not an identity matrix, but this is very close to an identity matrix. So the off-diagonal entries are almost close to 0, and the diagonal entries are close to 1. So this is a very interesting property. And this says that you don't have to spend much complexity or time or power in channel estimation. So we are going to exploit this particular property and construct a graphical model with which we can perform demodulation with even at a lower complexity. Okay. So what we are going to do is we are going to work on a new model. Instead of y is equal to hx plus w, we'll have a newer model, and that model is constructed by just simply taking H transpose multiplied along this entire system. So once we have this,
sorry to interrupt. So, but even in the equation, whatever we have written, H transpose Y, when you multiply, then again that requires CSI at the receiver, right?
Right. So that's a good question. So you mean when you multiply H transpose, you need this information, H transpose, right? Right. So in order to get away with this, what we would do is we'd use the previously transmitted Y. So we still need CSI, but we'll not explicitly estimate H. So what we'll do is we'll have a pilot phase. So in the pilot phase, let's say this is pilot and this is data. So in the pilot phase, I'll transmit some identity matrix. That is X will be equal to something of this form.
Okay.
Now, let's say I receive something YP here. Okay. So YP will be H times identity matrix times some noise. Now, instead of H transpose, what I'll actually use is I'll use YP transpose.
Okay. Got it. Yeah, that's what I was bit. Yeah, because I thought when we increase the dimension of H, so it means that when random matrices, that becomes the columns of H becomes close to orthogonal to each other.
Correct. Correct. Exactly.
That behaves like an orthonormal matrix.
Correct.
A matrix, but yeah, that's what I was confused. Again, we need this CSI. Okay, got it.
Correct. So we use this. So in fact, it so turns out that instead of estimating H and we using this actually improves the performance because the YP transpose H gives us a biased estimate of H. So typically when we estimate H, we'll have an unbiased estimator. I'm not going into the details of this, but if we analyze, then YP transpose H gives us a biased estimate of H. And that bias actually helps us to reduce the mean square error in the channel estimation. So yeah, this actually helps us in improving the performance of the system when the channel knowledge is not perfectly known. Okay. Anyway, I'll not get into the details of channel estimation because that does not come under the graphical model aspect.
Yes.
Yeah, that's a good question. Yeah. Okay. So once we have this new model, then we have a matrix J, which is very close to an identity matrix. And the off-diagonal terms are very close to 0, and the diagonal terms are very close to 1. And we need to identify what are these xi's, the usual values. But one thing that to note here is this J is always a square matrix. Earlier, we had a H matrix, which could have been even a rectangular matrix. But in this case, this J is always a square matrix, and the diagonal terms are always going to be very close to 1. And so in this case, once again, we need to identify what are the factor nodes and the variable nodes. The variable nodes are quite straightforward. So we have 2k variable nodes. Okay, so these x1 to x2k, these are what we need to identify. So what are the factor nodes here? So since this is a diagonal matrix, obviously the factor nodes or the observations that we have are exactly equal to the same number as the variable nodes. In this case, it so turns out that the factor nodes that we have here, so we have zi's, right? So these zi's are the factor nodes. So we'll apply the same Gaussian approximation that we did before. So we'll write the zi's as some xi plus the interference term. And this interference term, we will use the Gaussian approximation and then approximate them to be Gaussian. And this ji's, we can approximate them to be 1. And what we need to identify is the statistics of this interference term. So as before, what we need to do is just estimate the mean and variance. Once we know the mean and variance, we are done with identifying the messages. All we need to do is just get the mean and variance. So the interesting aspect is if we just assume that the so I think this example I've written only for xij is equal to plus or minus 1. this is this particular example is not for any constellation. So this is only for this 4QAM constellation, where the individual symbols are just plus or minus 1. The real and imaginary parts are plus or minus 1. So if we need to find out the mean, then the mean of these are nothing but 2pj minus 1, where pj is the probability of xj is equal to plus 1. So yeah, so the probability of this xj is equal to minus 1 is 1 minus pj. So the mean is plus 1 times pj into minus 1 times 1 minus pj. We get 2pj minus 1. Similarly, we get the variance here. So all we do here is once again compute the likelihood, and with this likelihood, we compute the posterior probability, and that is the posterior probability here. So just as before, what we do is compute the likelihood and posterior and keep updating. So we just transmit the posterior probabilities from the variable nodes, and the variable and the factor nodes here compute the likelihoods. So these are the likelihood computation at the factor nodes. So the interesting thing here is, once again, what is the interpretation? So the interpretation here, the likelihood interpretation is still the same, but the posterior probability interpretation is slightly different here, because here, because of this approximation that that we have here, we can almost approximate it to 1. The posterior almost turns out to be the probability of x being j, or probability of x being plus 1 or minus 1. So this is just as good as being the individual probabilities itself. So if I want to do a maximum likelihood estimator, or maximum likelihood detector, or maximum likelihood map detector, all I need to do is just compute this probability. So essentially what we are doing is we are computing the probability of the actual variable itself being plus 1 or minus 1. So this as a simplified computation compared to the previous computation. So earlier we need to compute these mean and variance separately, and that involved further computations inside. But in this case, we can approximate this to be 1, and these things, the statistics of the off-diagonal terms need to be computed. So only from these, the computation of the messages are simplified, much simplified compared to the earlier one. So this is exactly the same as the previous sum product algorithm, but with certain simplifications, and that simplification comes from the application of this random matrix theory properties of channel hardening and so on. And the interesting aspect here is that this one converges much, much faster. So if we see here, the earlier algorithms required some 80 to 100 iterations to converge, whereas this channel hardening exploiting message passing algorithms, they converge within 15 to 20 iterations, maximum of 20 iterations. Sometimes when the loading factor is very small, that is, loading factor is small means the system is over-determined. There are only 16 unknowns, but we have 128 observations. It converges within 5 iterations. Whereas if the loading factor is 1, that is fully loaded, 128 unknowns and 128 observations, it converges roughly at 16 to 17 iterations. So the convergence of this system is much faster compared to the earlier message passing algorithm. That is because earlier we had a lot of interference. We didn't take into account that the channel matrix itself looks almost like an orthogonal matrix. We didn't take into account that information. Because of that, there was a lot of interference that needs to be computed and cancelled out. Whereas here, because we had somehow used that information and then took a channel matrix which is almost close to a diagonal matrix, the convergence is much faster, and then within less than 20 iterations we converge, and this gives a complexity which is really, really small. So comparing here for n is equal to 256, once again we see an order difference. This channel hardening exploiting message passing algorithm requires roughly 76 million computations. This is, I think, for 16 QAM. Whereas MMSE requires 157 million computations. So this computation is huge, as in the computational difference is huge. Once again, an order of difference that we see here. So this makes, once again, life simpler. And yeah, once again, here we see a performance which is very close to what we saw earlier. And once again, an interesting thing to note here is in the earlier, what we saw is we saw performance close to the theoretical best at 256 when the dimensions were 256. Whereas when we exploit further properties of the large dimensional systems, then we get close to the theoretical best even at a smaller dimension, that is 128. So even with 128 dimensions, when we exploit the property of large dimensions, then we see that we can get much closer using this probabilistic graphical model demodulation. And another advantage, again, there are only two advantages that we keep repeatedly mentioning here. One is the computational complexity, other one is the near optimum performance. So here we have compared the computational complexity with the, or rather the, okay, this shows both the computational complexity in some sense and the performance. So we are plotting here the SNR required to achieve 10 power minus 3 BER by the three different decoders. One is the MMSC decoder, other one is the channel hardening exploiting message passing algorithm, other one is the spear decoder. So spear decoder interestingly stops when the number of antennas are roughly equal to 16. Because beyond this, spear decoder becomes exponentially complex to run. We cannot even run this beyond this particular point. So this is the best we know so far. We cannot know beyond this because it is impossible to run spear decoder. Whereas we can run both the MMSE and the message passing algorithm. But the MMSE requires huge SNR. So the gap in MMSE is almost as seen before 10 dB. That is at high number of antennas. And if you go for smaller number of antennas, the gap is slightly smaller. But typically, the gap between the message passing algorithm and the MMSC algorithm is almost 10 dB. And the message passing algorithm, as the number of dimensions increase, it gets very close to the theoretical best. So this is the theoretical best, which is achieved by spear decoding quite earlier. I mean, if it was if we were able to run the spear decoder, it achieves quite earlier. But then our message passing algorithm achieves this roughly at 128 number of antennas. So this is what we see. And yeah, I think this is similar to what we saw. Okay. Now, we saw message passing algorithm for decoding LDPC codes, that is for error correcting. And then we saw a message passing algorithm for demodulation. Typically, all systems have to demodulate and then they have to decode. So both the algorithms, if they were anyway message passing algorithm, is it possible to combine them? So because both are message passing, both are graphs, why can't we combine them? It so happens that it is possible to combine them. So we have what is known as this joint graph or joint graphical model, where there is one huge graph. The huge graph typically represents the LDPC part because the LDPC code word sizes are huge. They are typically in the orders of thousands, whereas the antennas are typically in the size hundreds. So we'll have multiple blocks. So we'll have multiple blocks of received signals. So let's say the LDPC code size is 1000 and we have 100 antennas. So that means we'll have to wait till we get 1000 received symbols. So we'll wait for 10 different time instances. In 10 different time instances, we would have collected 1000 different, or we would have collected 100 symbols, which all put together will give 1000 symbols together. So with all these received signals that are obtained over time and space, we can construct a huge joint graph with three different node sets. So one is the set of factor nodes, or sorry, one is the set of variable nodes that correspond to the LDPC code word, and one is the variable node that correspond to the received. Sorry, I think I've interchanged this one. Okay, so these are the LDPC check nodes. So these are the factor nodes that correspond to LDPC factor nodes. And these are the variable nodes of LDPC. And these variable nodes of LDPC also act as the variable nodes of the demodulation. And these are the observation nodes or the factor nodes of demodulation. So these are observation or factor nodes for demodulation. So because these variable nodes are common between both the LDPC decoding and the demodulation, what we can do is we can in fact combine these together. Because of this combination, once again, there is a reduction in complexity, in computational complexity. Had there not been this combination, then we'll have this graph separately and this graph separately. Once again, the messages would have been computed here separately and there separately. And there is almost twice the, or at least the messages that are computed at the variable nodes, they would have been computed twice separately. Now here what happens is messages that are computed at the factor nodes of the demodulation, they are sent to the variable nodes. And these variable nodes will take into account the messages from both the factor nodes from the LDPC side, factor nodes from the observation side. And then they update their internal summary. And this is what has sent us the message from the variable node to these factor nodes as well as these factor nodes. So there is an effective communication between this factor nodes and the factor nodes of the LDPC side and the factor nodes of the demodulation side. In some sense, what is happening is the turbo decoding. So those who are aware of turbo literature, they would know that there would be some convolution code which is used in turbo codes. And there will be a convolutional decoder. So this will be a convolution decoder. And there will be a demodulator. So the demodulator will demodulate and send the information to the decoder. The decoder will use the convolutional decoder or convolutional codes decoding and then correct some errors. And with that, it will send the information back to the demodulator. And then there's a turbo passage of information here where the demodulation and decoding, they run iteratively in a loop. So that means whatever is corrected in the bit level is sent back to the demodulator, and that is again corrected in the symbol level. So that's the advantage in the turbo codes. So a similar thing is implicitly happening in the joint graph of this detector decoder. Here, what happens here is the advantage of LDPC code is directly brought in by demodulation. Whatever extra information that is given by the LDPC code is passed on through the factor nodes of the demodulation through this variable node connection. So this also speeds up convergence as well as reduces the computational complexity a lot. So the final graph this big graph that we construct is once again based upon the a posterior probability. So we have this as the likelihood, where this x is the actual variable node, s is the set of check nodes, and y is the observation. So we can write this as proportional to this joint probability. Once again, we factorize them as this three different. Remember, till earlier we had only this much, or rather, either we had this or we had only this. Now we have three different factors or three different set of nodes to have. That is S one set of nodes, Y another set of nodes, and X as another set of nodes. And we are combining them together to form. Now this is a tripartite graph. Earlier we had a bipartite graph. Now we have a tripartite graph. And even though this is a tripartite graph, we consider these two sets to be as factor nodes and still a variable node. And the same earlier, whatever rule that we saw, we use the same rule to compute the messages from factor nodes to variable nodes. Once again, we just multiply all the messages and apply the factor that we have at that particular factor node. And at the variable node, we just simply multiply all the incoming messages. Same rule. Only thing, the graph has differed here. So that the graph is a tripartite graph. We have two different sets of factor nodes. But the same sum product algorithm could be applied here. And if what we see here is, so I'm showing the performance here. It happens that we get almost 1 to 2 dB difference in performance when we combine these things together. So traditional LDPC codes, you just apply them, demodulate them separately and decode them separately. There is some loss of performance, or at least the convergence rate is very small. So once again, here we have large dimensions. We have 128 antennas and 11,520 is the code length of the LTPC code, which is the rate of code. And when you apply this joint decoding, you get more than 1 dB. So this is roughly 1.7 dB or 1.6 dB difference in the performance. And it goes very close to the theoretical minimum capacity that is possible at this particular hardware resource. There is one more, probably will come to this later when we have time. So there is something called as exit chart analysis. So this tells us how the information is being transferred from one set of node to another set of node. So it connects or it relates the mutual information at one set of node to the mutual information at the other set of node. And this is known as the extrinsic information transfer. So the extrinsic information transfer is abbreviated to exit. So this tells us how the information is being transferred from one set of node to another set of nodes. So this IA represents the mutual information between the variables and the posterior probabilities, and this IE represents the mutual information between the variables and the likelihoods that are computed. So given this mutual information as the input, how much extrinsic information, mutual information does this graph produce? That is captured by this function. This f is known as the exit function. And this exit function depends upon each and every graph. So if I have one factor graph, let's say a factor graph of this kind, some connections, and so on, then I'll compute the mutual information at this particular set of node. And if I feed this mutual information to these factors, then how much new mutual information or how much extrinsic information is it producing? That is given by IE. This is the mutual information at the variable node. And the information that it produces is given by this function fa. So this f is what that is used to theoretically analyze the graphical models in terms of information theory. So when we combine two different graphical models like this, then we can also learn how much information is processed by this set of nodes and how much information is processed by these set of nodes. Okay? And here we have a way of combining two different graphical models and identifying how the information is being transferred from one set of nodes to another set of nodes. So, the top curve here is the information that is being, this is, okay, I'll probably explain the left-hand side first. So this shows that if I feed in this much of mutual information to the graph, then it produces this much of external information. And eventually this information goes to 1. That means that that's the maximum producible information. Okay. So here what we have done is we have combined together, superimposed the exit chart of the, so the first one is the check nodes graph, that is the top graph, the LDPC part, and the bottom one is the joint variable node part, that is the demodulated part. So we have two different graphical models combined together. So this first produces 0.7 of mutual information, which is fed into the other one, and that produces some external information, which is once again fed in back, and this is known as the decoding trajectory. So each set of graphical model nodes, that is each set of observation node and or each set of factor node and the variable node, when the messages are passed between them, they provide some extra information or they refine the probabilities. And those refined probabilities are once again refined by the other set of variable nodes and factor nodes. And how much do they refine is given by this graph. So we can construct graphical models, or rather we can construct LDPC codes by looking into this gap. So the smaller is this gap, the better is the decoding performance, or better is the SNR. So as SNR increases, what happens is this gap becomes wider and wider. So there is huge information that is obtained just by one iteration. So that's why as SNR increases, we see that the gap increases. So if we can have this gap to be really small at a very low SNR, then it says that, so let's say at SNR is equal to 1 dB, the gap is very small. And beyond that, the gap goes on the negative side. So that is, this curve goes above the other curve, then the decoding is not possible, then we'll always have error. So ideally what we would want is these two curves meet at as low SNR as possible. So if these two curves are close together at very high SNR, then it means that the decoding is successful only at high SNR. So ideally what we would want is to have these two codes or these two curves meet each other at as low SNR as possible. So we could tweak this by constructing an LDPC code which has this curve as high as possible. By learning what is this code, we could construct an LDPC code. So this becomes an LDPC code construction problem. So the interesting aspect here is that by learning how these graphical models perform, we can also construct very good error correcting codes. So not only this helps us in estimation and inference, but this also helps us to do code design. That's the interesting aspect of this, what I want to highlight here. Okay. So finally, I'll talk about what is known as this generalized spatial modulation. So generalized spatial modulation is one type of modulation where we have NT different antennas at the transmitter, but not all the NT antennas are simultaneously turned on. There are only a subset of these NT antennas. For example, if we had NT is equal to 4, then at any point of time, only some subset, let's say that subset size is 2, what is known as NRF here, that is RF chains. This NRF represents RF chains, that there are only 2 RF chains here. So at any point of time, only 2 of these antennas are active. So which 2 are active depends upon what is the input bit. So typically what would we do is, if we have NT antennas, we would put symbols in all the NT antennas. If we have 4 antennas, we'll transmit 4 different constellation symbols, right? So instead, what if we transmit only 2 different constellation symbols? But then in which 2 antennas do we transmit? That could be selected by the input bits. I'll probably explain this with an example. So let's say that we have BPSK constellation and 2 RF chains and 4 transmit antennas, the same configuration that we have. Then let's say with every 2 bit of information, let's say the first 2 bits given to me, I'll say I'll choose 2 BPSK symbols. Once I have these 2 BPSK symbols, the next thing is I need to know which antennas. I have 4 antennas, which antennas should I put in? So the possible combinations are 4C2. So that is, there are 6 ways in which I can transmit these 2 BPSK symbols. So if I have another 2 bits to choose which of these 6 possible antennas or patterns that I can use for transmission. So I'll choose another 2 bits. So these 2 bits will, let's say, these are the possible values. So I can say 0, 0 means then I will activate the first antenna and second antenna. And if 0, 1 comes, then I'll say I'll activate the first antenna and third antenna. If I get 1, 0, then I'll say I'll activate the first antenna and fourth antenna. For 1, 1, I'll say I'll activate the second and third antenna. So these are the activation patterns. So this is known as generalized spatial modulation. What we are doing here is we are modulating not only the power, but also modulating the space. That is turning on and off the antennas depending upon what is the input bits. So we'll divide the input bit into 2 different streams. One stream will decide what constellation to transmit, and another stream will decide what antenna to activate. So this is known as the generalized spatial modulation, GSM. Why is this called generalized? Because there is another scheme known as spatial modulation where we always transmit only one constellation symbol. That is, only one antenna is always activated. That is known as spatial modulation. When you have a subset of antennas to be activated, then it is known as generalized spatial modulation. Okay. Now, the advantage of this generalized spatial modulation is First and foremost is the hardware advantage. Even though if you have NT transmit antennas, the number of RF chains that you have is lesser than NT, which means your hardware complexity is very, very small. And the rate that you get compared to spatial modulation is also either higher or just as much as the same rate. So in this particular example, you get 4 bits to be transmitted by each and every transmit symbol. Whereas if I had used the regular spatial multiplexing scheme and used BPSK, I would have used 4 antennas. And then in each of those antennas, I would have transmitted 1 BPSK symbol, which means I would have again gotten 4 bits. So the rate is same as the generalized spatial modulation also offers 4 bits, this 2 bits plus these 2 bits. But I have hardware complexity reduced by 50%. I have only 2 antennas and only 2 RF chains. If I have 2 RF chains, that means the local oscillator, the amplifier, everything is reduced by half. The power that is transmitted, everything is reduced by half. The hardware complexity is reduced by half, but the rate is the same. So that is the biggest advantage of the generalized spatial modulation. And the most counterintuitive thing is the performance of this spatial modulation is much better than the spatial multiplexing. So I'll not get into the theory of it, but I'll just show the simulation result that we have. So here we are just comparing all possible combinations. So we have here an 8x8 system, that is 8 transmit antennas and 8 receive antennas. So 8 is number of transmit and receive antennas. And if we use BPSK here, we get 8 bits per second per hertz. That's our spectral efficiency. So this red curve here, that's the V-blast or the spatial multiplex. That's the traditional spatial multiplexing scheme that is used in all MIMO systems. Now, this is the performance that we have, and all systems that here have 8 bits per second per hertz. Now, the performance of spatial modulation, where we have only 1 transmit antenna to be active at any point of time. That is, only 1 RF chain is there in the system, which means there is 8 times reduction in the hardware complexity. Whereas the performance of that is really bad. Almost the best possible performance is almost 4 dB lesser, giving us 4 dB lesser requirement in power. And let's take the GSM system. So that is a generalized spatial modulation. So the GSM with 2 RF chains, with 2 active antennas and 4 QAM offers 8 bits per second per hertz. But that performance is better than the spatial multiplexing performance by almost, if I look at 10 power minus 5, then the gap is almost 1.2 dB. So the power requirement is lesser to achieve the same performance by 1.2 dB. And also more importantly, I require 4 times lesser antennas. That is 75% reduction in the hardware complexity. So with 75% reduced hardware, and hence the hardware cost is also reduced 75%. My performance is also better by 1.2 dB. So this is the most interesting aspect of GSM. So hardware cost is lesser, performance is better, and you get the same spectral efficiency. The data rate is not affected. Okay, so GSM is a really good scheme, but the problem is, how do we decode GSM? Now, can we use the same probabilistic graphical models method that we have earlier? If you remember earlier, what we did was we just said if we had NT transmit antennas, then each of them were 1 variable. And we assumed that the symbols transmitted in each of these variable nodes were actually independent of each other. But whereas in GSM, they're not independent of each other. If at any point of time, only a subset of them is active, which means that there is a dependence between the variable nodes itself. Is it possible to, ideally, it looks like you cannot use the graphical models method to decode this. But it so happens that by doing a slight modification, we can in fact use the probabilistic graphical models. All we need to do is use another layer. Okay, just like how we had this joint detection and decoding where we introduced another set of factor nodes, all we need to do here is introduce another set of factor nodes. And what is that factor node? So we introduce what is known as the antenna activity indicator. So what is this antenna activity indicator? So for every xi, we write them as some ai times this transmitted symbol s. So this ai is 0 if the antenna is not active, or 1 if the antenna is active. So whatever is this s will be just xi equal to s if ai is equal to 1. Otherwise, this is 0. Okay. So conditioned on ai, if I condition this x, probability of x given ai, then I can know exactly if this x will be 0 or not. So if I know a, I won't know what is the value of x if it is non-zero. But if I know that a is equal to 0, then I know for sure that this x is equal to 0. So what we have done is we have introduced another set of conditions, or like similar to what we had this check nodes. Now we have another set of activity nodes. So this activity nodes will simply say that if I have these many number of variables and I just compute the activity of these variables, the activity should be equal to NR. Okay, that is always fixed. So in a generalized spatial modulation scheme, the number of active antennas always is fixed. So the active antennas will add up to NR. Okay. So if all of them add up to, in our previous example, NR was 2, right? So I sum A1 plus A2 plus A3 plus A4, they should be equal to 2. So this is exactly similar to the check nodes that we had in LDPC case. So remember the variable nodes, if they all add up to 0. So that was the condition that we had in the LDPC case. Similar to that, here we are adding one condition, and that is the activity condition, which simply says that the activity patterns should all add up to the number of RF chains. So based on this, once again, we have another factorization with 3 different set of nodes. One is the observation, another one is the variable, another one is the activity, which is equivalent to the check node. So we construct, once again, similar to the previous case, a layered approach where we have a common variable node, but have 2 different factor nodes. One set of factor nodes, which actually in this case represent the observations, the variable nodes, and these are the activity nodes. And this is technically not a node, it just this says NR. That's all. You can just change this number. So there is actually only one node, so one set of nodes here. Okay. So these are the activity nodes. So once again, how we constructed the messages earlier, we can do the same construction here. So the variable nodes simply multiply the messages that come in from all the factor nodes, and the factor nodes just take in all the messages from the variable node and then apply their factor. So we do the computation here, and once you compute, we can do a similar demodulation here. I'm just showing the results. So once again, we compare it with MMSE, and this is really amazing performance, because the MMSE gives very, very bad performance because MMSE does not take into account the structure in the transmit signal. So because the GSM has only NRF active antennas, that structure is not taken into account by MSE, and it gives very poor performance. Whereas this structure could be taken into account by introducing another layer and doing some kind of joint demodulation. And once again, by using this layered message passing, we see that the performance of the GSM decoding using probabilistic graphical models is really, really good. So this gap is almost 5 dB. But if you see at 10 power minus 5, this gap will be really, really huge. So this curve will go somewhere like this. This gap will be almost roughly equal to 20 dB. So compared to MMSE, this message passing algorithm, complexity also, we already saw that this is almost 1 order lesser. Now we also see the performance is really good. So the interesting aspect here is for index modulation, the probabilistic graphical model based receivers are much, much better and low complexity and very high in performance. So I'll probably stop here. I have another section for multi-user systems, but multi-user index modulation systems, but I think because of time constraint, I'll stop here. So essentially what we have seen is, I'll just quickly summarize what we have seen. So the main idea is the sum product algorithm. The main idea that if someone wants to see as a takeaway from this talk, is to see any inference problem as a factor graph. And this factor graph is constructed using an objective function. Typically, either it is the likelihood or the posterior probability, which we want to maximize. From this objective function, we construct this factor graph. And over this factor graph, there are two simple rules of computing messages and using these messages, pass them back and forth, and then at some point of time, have some kind of a stopping criteria to stop the messages. And from that, just perform this objective function calculation and perform the inference. That's all this. This is a very simple algorithm. And we saw three different applications. One was the LDPC code decoding. Another one was MIMO demodulation. And we saw how to combine these two. And then using that combination, we also applied that to index modulation decoding, where we decoded index modulation symbols using graphical models. I'll probably stop here. Yeah, if there are any questions, please.
Yeah, I will ask the audience. Before that, Lakshmi, so that GSM with the factor graph, is there any paper have you published based on that work?
Yeah, there is a paper. I'll send the reference to you.
Yeah, just I want to know the details, how the GSM decoding can be done with the factor graphs.
Sure. I'll send the reference.
Or maybe if it is in a website, I can take it. You have mentioned that in your webpage, that paper?
It is there. So it.
Okay. Then I will.
It will be on the capacity and performance of generalized spatial modulation. That will be the title of the paper.
In the TCOM or TWC?
It's a letter. It is actually a communications letter.
Okay, I will take it. Okay. So any other questions from the participants? Yeah, okay. Okay, Lakshmi, thank you very much. So I don't think they have any questions. And so thank you very much. That too, you have extended your time until the late evening.
Thank you. Thanks for inviting me.
Yeah. Yeah. Okay, Lakshmi, I will get in touch with you to collaborate in some other future option.
Sure.
So,
Yeah.
Okay. Thank you very much.
Sure. Thank you. Thanks for inviting. Bye.